Between the spiral arms of the Milky Way and the approaching disk of Andromeda lies a distance so vast that light itself requires 2.5 million years to cross it. At this moment, photons that departed Andromeda when the first members of the genus Homo were learning to shape stone tools on the African savanna are only now arriving at Earth, carrying ancient news of a galaxy that has been hurtling toward us the entire time. The void between these two cosmic islands appears, to every instrument we possess, as the purest emptiness imaginable. No stars burn there, no planets orbit, no civilizations could possibly exist in that lightless abyss. For centuries, astronomers dismissed this space as precisely what it seemed: nothing. They were profoundly wrong. Here is what will overturn everything you believe about the emptiness between galaxies. The space separating the Milky Way from Andromeda is not a vacuum. It is not void. It is a structure so vast and so subtle that we have only begun to perceive its contours in the last 2 decades. Diffuse hydrogen halos extend from both galaxies like invisible breath, reaching toward each other across the darkness. Filaments of dark matter form a gravitational scaffold connecting the two, an architecture of mass that bends light and shapes the motion of everything it touches. Rogue stars, flung from their home galaxies at velocities exceeding 1 million miles per hour, sail through this supposed emptiness on journeys that will last longer than the current age of the universe. And slowly, imperceptibly, this entire region is collapsing. The two galaxies are not merely neighbours across an abyss. They are partners in a gravitational dance that began billions of years before Earth existed, and their eventual collision will transform everything we think we understand about the in-between. If you find yourself drawn to discover what truly fills the space everyone else dismisses as void, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let us cross into the darkness between galaxies. The night sky, on the clearest evening in the most remote location on Earth, reveals approximately 2,500 stars to the unaided human eye. Each of these points of light represents a sun, many of them orbited by planets, all of them bound by gravity to the same vast wheel of stars we call home. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, a number so large that if you counted 1 star per second without pause for sleep or rest, completing the tally would require between 3,000 and 12,000 years. Our galaxy spans roughly 100,000 light-years from edge to edge, meaning that light departing from one rim would not reach the opposite side until humanity had risen, flourished, and perhaps fallen 1,000 times over. This is an incomprehensibly vast structure. It dwarfs anything the human mind evolved to grasp. The entire sphere of Earth's radio transmissions, expanding outward since Marconi's first deliberate signals in 1895, has grown to perhaps 250 light-years in diameter. This shell of human communication, containing every broadcast, every satellite transmission, every electromagnetic whisper of our technological civilization, represents less than 1/4% of the galaxy's diameter. We have been screaming into the cosmic darkness for over a century, and our voice has barely left the neighbourhood. Yet the Milky Way, for all its enormity, is merely one island among billions, and the nearest major island lies 2.537 million light-years away. The Andromeda Galaxy, known to astronomers as Messier 31 or simply M31, is the most distant object visible to the naked human eye. On a moonless night far from city lights, it appears as a faint smudge of light in the constellation that bears its mythological name, a blur that early astronomers dismissed as a nearby cloud of luminous gas. The truth, revealed gradually through centuries of improving observation, proved far more startling. That faint smudge is not a cloud. It is an entire galaxy, larger than our own, containing roughly 1 trillion stars. It is a spinning disk of matter spanning 220,000 light-years, surrounded by dwarf satellite galaxies and globular clusters, embedded in a halo of dark matter extending far beyond its visible boundaries. It is, in nearly every respect, a sister to our own cosmic home. And between these two great spirals lies a distance that reduces every human achievement to insignificance. Consider the speed of Voyager 1, humanity's most distant spacecraft. Launched in 1977, it has spent nearly half a century travelling outward from Earth at approximately 38,000 miles per hour. At this velocity, which represents the fastest any human-made object has ever travelled away from the Sun, Voyager 1 would require roughly 449 billion years to cross the void between the Milky Way and Andromeda. This is more than 32 times the current age of the universe. The entire history of cosmic evolution, from the Big Bang through the formation of the first stars, the birth of galaxies, the appearance of life on Earth, and every moment of human civilization, could replay 32 times before Voyager would complete this single crossing. The fastest spacecraft humanity has ever built, NASA's Parker Solar Probe, reaches velocities exceeding 430,000 miles per hour as it dives close to the Sun, siphoning gravitational energy from our parent star. Even at this blistering pace, 11 times faster than Voyager 1, the journey to Andromeda would require roughly 38 billion years. The Sun will exhaust its hydrogen fuel, expand into a red giant, consume the inner planets, and collapse into a white dwarf, all before a Parker Solar Probe could travel 1/6 of the way to Andromeda. These numbers crush any hope of conventional transit. They reveal a truth about intergalactic distances that even seasoned astronomers sometimes fail to internalize. The space between galaxies is not merely large. It is a prison of scale from which no chemical rocket, no ion drive, no nuclear pulse propulsion system could ever permit escape within any meaningful time frame. The energy requirements for accelerating a spacecraft to velocities that could cross such distances in less than geological time exceed the total energy output of our Sun over its entire 10 billion year lifetime. This is the void that astronomers have historically dismissed as empty. This is the darkness they treated as absence. They looked at the space between the Milky Way and Andromeda and saw nothing worth studying, no light to measure, no spectra to analyse, no objects to catalogue. The void was defined by what it lacked, but absence of light is not absence of matter. Darkness is not emptiness, and the void, it turns out, is full. The first hints emerged from observations not of the intergalactic medium itself, but of how distant light passed through it. In 1970, astronomers began systematic studies of quasars, the extraordinarily luminous nuclei of distant galaxies powered by supermassive black holes devouring matter. These cosmic beacons are so bright that their light can be detected across billions of light years, and as this light travels toward Earth, it passes through any intervening material. Each cloud of gas, each filament of matter, each accumulation of hydrogen between the quasar and our telescopes leaves its fingerprint on the spectrum. What researchers found defied the expectation of empty voids. The spectra of distant quasars revealed absorption lines, characteristic frequencies where specific wavelengths of light had been absorbed by intervening matter. These lines appeared in such profusion that astronomers named the phenomenon the Lyman alpha forest, after the specific hydrogen transition responsible for most of the absorption. The forest was dense, it was ubiquitous, and it revealed that the supposedly empty space between galaxies was permeated by hydrogen gas, invisible to direct observation but absolutely present, leaving its unmistakable chemical signature on every beam of light that traversed the cosmos. This hydrogen exists in several forms, each revealing different aspects of intergalactic structure. Much of it consists of ionized hydrogen, atoms stripped of their electrons by the relentless ultraviolet radiation that permeates cosmic space. This diffuse ionized medium fills the voids between galaxies at densities almost incomprehensibly low, typically less than 1 hydrogen atom per cubic meter. To visualize this emptiness, consider that the air you're breathing contains roughly 25 quintillion molecules per cubic centimeter. The intergalactic medium is approximately 100 trillion times less dense than this. It represents perhaps the best natural vacuum in the known universe. And yet, across the staggering volumes involved, even this rarefied gas accumulates to vast mass. The total amount of hydrogen in the intergalactic medium likely exceeds the total mass of all the stars in all the galaxies combined. The void is not empty, it is simply spread thin, its contents diluted across distances so immense that local emptiness becomes cosmic fullness when integrated over sufficient volume. But the diffuse intergalactic hydrogen between random galaxies represents only the beginning of what fills the space between the Milky Way and Andromeda. These two galaxies are not distant strangers separated by undifferentiated void. They are gravitationally bound partners, locked in an orbital relationship that has persisted for billions of years. They form the dominant members of a structure astronomers call the Local Group, a collection of more than 80 galaxies spanning roughly 10 million light-years, and the space binding this group together is far from uniform. Beginning from the visible disk of the Milky Way and extending outward, successive shells of increasingly diffuse matter reveal themselves to instruments sensitive enough to detect them. The first of these is the galactic corona, a spherical halo of hot gas extending roughly 300,000 light-years from the galactic centre. This gas, heated to temperatures exceeding 1 million degrees Kelvin, was discovered through its X-ray emissions and its effects on the light of distant quasars. It represents the extended atmosphere of our galaxy, the outermost boundary of the Milky Way's direct material influence. Beyond the corona, the circumgalactic medium extends further still. This region, reaching out to roughly the virial radius of the galaxy, perhaps 600,000 light-years from the centre, contains gas at a wide range of temperatures and densities. It includes material actively falling inward toward the galactic disk, fresh fuel for future star formation. It includes material flowing outward, expelled by supernovae and the energetic processes surrounding the central black hole. It includes gas that has been cycling between infall and outflow for billions of years, never fully joining the disk, never fully escaping to intergalactic space. The circumgalactic medium of the Milky Way does not end sharply. There is no crisp boundary where galaxy ends and void begins. Instead, density decreases gradually, transitioning through ever more rarefied conditions until the circumgalactic medium of our galaxy meets the circumgalactic medium of Andromeda somewhere in the vast darkness between. In 2015, a team of astronomers led by Nicholas Lehner at the University of Notre Dame published observations that transformed our understanding of Andromeda's extent. Using the Hubble Space Telescope's cosmic origin spectrograph, they analysed ultraviolet light from 18 quasars whose sightlines passed through different regions around Andromeda. The absorption signatures revealed something remarkable. Andromeda's halo of circumgalactic gas extends at least 1.3 million light-years from its centre, and likely reaches as far as 2 million light-years. This distance must be absorbed slowly to appreciate its meaning. If Andromeda's gaseous halo truly extends 2 million light-years, and the Milky Way possesses a comparable halo extending perhaps 600,000 to 1 million light-years from its own centre, then these two halos are not separated by a void at all. They are already touching. They are already interpenetrating. The space between the visible spiral disks of these two great galaxies, the void that appears so black and so empty in every astronomical image, is in fact already occupied by the overlapping atmospheres of both galaxies, diffuse tendrils of hydrogen reaching across the darkness to mingle in the middle. The halos are not the only structures that fill this seemingly empty space. They are merely the baryonic component, the ordinary matter made of protons, neutrons and electrons that participates in electromagnetic interactions, and can therefore, with sufficient sensitivity, be detected. But ordinary matter represents less than 5% of the universe's total mass energy content. The dominant component, accounting for roughly 27%, is dark matter, a form of mass that does not emit, absorb or scatter electromagnetic radiation, making it invisible to every telescope and detector designed to capture light. Dark matter reveals itself only through gravity. Its presence is inferred from the motions of visible objects, the rotation curves of galaxies that spin too fast to be held together by their visible mass, the gravitational lensing that bends the light of background objects, the dynamics of galaxy clusters whose constituent galaxies move faster than their visible mass could permit. These gravitational signatures point consistently toward a universe filled with mass that we cannot see, mass distributed in vast halos surrounding galaxies and, crucially, for understanding the space between the Milky Way and Andromeda, in filaments connecting galaxies to one another. The distribution of dark matter in the universe is not uniform. Cosmological simulations, beginning with the pioneering N-body calculations of the 1980s and continuing through modern supercomputer models like the Millennium simulation and illustrious TNG, consistently produce a characteristic structure. Dark matter forms a cosmic web, a vast network of filaments connecting dense nodes where galaxy clusters reside. The filaments themselves are not visible, but they form the scaffolding along which ordinary matter flows, the gravitational channels that guide the formation of galaxies and determine the large-scale structure of the cosmos. The Milky Way and Andromeda are connected by such a filament. This is not speculation. The gravitational influence of the two galaxies on each other, combined with observations of their satellite populations and the distribution of smaller galaxies in the local group, allows astronomers to infer the existence of a dark matter bridge stretching between them. The two galaxies are not isolated masses floating in undifferentiated space. They are nodes in a web, connected by an invisible ridge of gravitating matter that extends through what appears to be void. The dark matter filament between the Milky Way and Andromeda is not dense by any terrestrial standard. Its density is perhaps 10 to 100 times the average cosmic dark matter density, itself extraordinarily low by any measure. But it provides a continuous gravitational structure, a corridor of slightly enhanced mass threading through the intergalactic medium, and along this corridor the future of both galaxies is already being written. Because the Milky Way and Andromeda are not merely sitting across the void from one another, they are approaching at a velocity of approximately 68 miles per second, or 110 kilometers per second. This is roughly 100 times faster than a rifle bullet, a closing speed that translates to approximately 1.4 billion miles per year. The distance between the galaxies shrinks by an amount equal to Neptune's distance from the Sun every 6 months, and yet, even at this velocity, the approach is imperceptible on human timescales. At 68 miles per second, the time required to cross 2.5 million light-years is approximately 4 to 5 billion years. This is almost exactly the expected remaining lifetime of the Sun before it exits the main sequence and begins its transformation into a red giant. The collision between the Milky Way and Andromeda will occur, if our models are accurate, at roughly the same cosmic moment when the Sun begins to die. But the collision itself will not resemble the violent crash the word implies. The stars within both galaxies are separated by such vast distances relative to their sizes that direct stellar collisions will be extraordinarily rare. Each star is roughly the size of the Sun, roughly 865,000 miles in diameter. The average distance between stars in the Milky Way's disk is roughly 4 to 5 light-years, or about 25 trillion miles. If you scale the Sun down to the size of a grain of sand 1 millimeter in diameter, the next nearest star in this model would be located roughly 4 miles away. Galaxies are not solid objects, but rather swarms of stars, each member separated from its neighbours by distances that dwarf the objects themselves. When the swarms pass through one another, most stars will miss all other stars completely. The collision of galaxies is not a collision of bodies, but a collision of gravitational fields, a violent reorganisation of orbits rather than a shattering of matter. Stars will be flung outward by gravitational interactions. Others will plunge inward toward the merged galactic centre. The elegant spiral structures of both galaxies will be destroyed, their arms torn apart by tidal forces and reformed into a vast elliptical cloud of stars orbiting a common centre. Astronomers have already named this future structure Milkomeda. But long before the stellar disks interpenetrate, the halos will meet. Long before individual stars feel the gravitational tug of the approaching galaxy, the diffuse hydrogen atmospheres extending from both systems will begin to interact. This is not a future event. This is already happening. The circumgalactic halos of the Milky Way and Andromeda are already overlapping. The tenuous hydrogen extending from both galaxies already occupies the same regions of space. The collision, in a sense, has already begun. It is merely happening in regions so diffuse, so dark, and so distant from both galactic centres that no telescope has directly observed the interaction. Simulations suggest that as the halos compress and interact, shocks will form. The kinetic energy of the two gas masses moving through one another will convert to heat, raising temperatures in the intergalactic medium to tens of millions of degrees. This shock-heated gas will emit X-rays, a signature that future astronomers may detect as evidence that the collision has truly begun. But the most dramatic prelude to the merger involves objects even more exotic than diffuse gas, the hypervelocity stars. In 2005, Warren Brown and his colleagues at the Harvard-Smithsonian Center for Astrophysics announced the discovery of a star travelling so fast that it would inevitably escape the Milky Way's gravitational pull entirely. Designated SDSS J09J7455.2407. This star was racing outward at over 850 kilometers per second, roughly 1.9 million miles per hour. No orbit could bind it. No orbit. No gravitational well in our galaxy could contain it. This was a runaway, fleeing the Milky Way at a velocity that suggested a violent origin. The mechanism that produces hypervelocity stars was first proposed by Jack Hills in 1988. When a binary star system passes too close to a supermassive black hole, such as the 4 million solar mass monster residing at the centre of the Milky Way, tidal forces can tear the pair apart. One star falls inward, doomed to spiral into the black hole's accretion disk. The other is flung outward at tremendous velocity, carrying away the energy stolen from its companion's demise. This is not gentle ejection. This is a gravitational slingshot of the most extreme kind, capable of accelerating a star from typical orbital velocities to speeds that exceed the galaxy's escape velocity. Since that first discovery, astronomers have identified dozens of hypervelocity stars departing the Milky Way. Some originated near the galactic centre, flung outward by the Hills mechanism. Others may have been ejected by supernova explosions in binary systems, or accelerated by gravitational interactions in dense star clusters. Their trajectories carry them outward through the galactic halo and beyond, into the intergalactic void. And here is where the nature of the space between galaxies becomes profoundly relevant. These hypervelocity stars do not simply vanish when they leave the visible boundary of the Milky Way. They continue outward through the circumgalactic medium, through the overlapping halos, through the dark matter filament, into the space that separates our galaxy from Andromeda. Some of them, depending on their precise trajectories and velocities, are heading directly toward our sister galaxy. The journey, at even hypervelocity speeds, requires billions of years. A star travelling at 850 kilometers per second, maintaining that velocity across the entire intergalactic crossing, would require roughly 2.8 billion years to traverse 2.5 million light-years. This is less than the time remaining before the galactic collision itself. Stars ejected from the Milky Way today could arrive at Andromeda before the two galaxies merge, becoming immigrants to a foreign stellar population. And the process operates in reverse as well. Andromeda possesses its own supermassive black hole, larger than our own, estimated at roughly 100 million solar masses. This black hole, with its more powerful gravitational influence, should produce hypervelocity stars at a higher rate than our galactic centre. The stars it ejects are flung into the void between galaxies, and some of them are certainly heading toward us. The space between the Milky Way and Andromeda is therefore populated by stellar wanderers, suns without planets, travelling through darkness that will last for billions of years. These stars carry no planetary systems with them, having been stripped of any companions during their violent ejection. They shed no light on habitable worlds. They illuminate nothing but the diffuse hydrogen through which they pass, their stellar winds interacting weakly with the tenuous medium. Imagine the perspective of a hypothetical observer located on a planet orbiting one of these hypervelocity stars, though no such planet could exist. The sky would be utterly black. The Milky Way would appear as a faint smudge in one direction, growing gradually smaller over billions of years. Andromeda would appear as a faint smudge in the other direction, growing gradually larger with equally geological patience. The observer would occupy the most isolated vantage point imaginable within the local group, surrounded by diffuse hydrogen too thin to scatter light, embedded in a dark matter filament that exerts gravitational influence but emits no radiation of any kind. This observer would live in what most would call empty space, and yet the observer's star would be demonstrably not alone. The hydrogen halo would be present, detectable with sufficiently sensitive instruments. The dark matter filament would reveal itself through subtle gravitational effects on any test masses the observer cared to release. Other hypervelocity stars travelling parallel or anti-parallel courses would occasionally appear as points of light crossing the field of view, fellow travellers in the intergalactic wilderness. The void, from within, would reveal itself as a structure. The detection of this structure from Earth requires instruments of extraordinary sensitivity. The diffuse hydrogen in the circumgalactic medium does not glow brightly. Much of it is ionized, stripped of electrons by ultraviolet radiation, and ionized hydrogen emits primarily in wavelengths absorbed by Earth's atmosphere. Ground-based observations must rely on radio wavelengths, where neutral hydrogen emits its characteristic 21-centimetre line, or on ultraviolet observations from space, where absorption studies against background quasars reveal the gas indirectly. The development of these techniques has accelerated dramatically in recent years. The Cosmic Origins spectrograph on the Hubble Space Telescope, installed during the final servicing mission in 2009, has proven particularly powerful for probing circumgalactic and intergalactic gas through absorption studies. Each quasar observation provides a needle-thin probe through a specific column of intergalactic material, revealing the density, temperature, and chemical composition of whatever lies along the line of sight. By accumulating hundreds of such observations, astronomers have begun to map the diffuse structure of the local group. The emerging picture is one of profound complexity. The space between galaxies is not uniform. It contains streams and filaments, regions of higher and lower density, flows of gas falling toward galactic centres, and counterflows of gas blown outward by stellar feedback. It contains the debris of past galactic interactions, including the tidal streams of dwarf galaxies disrupted by the gravity of the Milky Way and Andromeda. It contains the extended halos of those surviving dwarf galaxies, the more than 80 smaller systems that populate the local group like minnows swimming among whales. One of these dwarf galaxies deserves particular attention, because it provides direct evidence that the space between the Milky Way and Andromeda is not merely occupied, but structured. The Triangulum galaxy, also known as Messier 33, is the third largest member of the local group, a modest spiral containing roughly 40 billion stars. It lies approximately 2.7 million light-years from Earth, slightly farther than Andromeda, and its relationship to Andromeda has been debated for decades. Recent observations, particularly high-precision measurements of Triangulum's proper motion, using the Hubble Space Telescope and the Gaia astrometric satellite, suggest that Triangulum may be a satellite of Andromeda, rather than an independent galaxy. Its orbit appears to carry it around Andromeda on timescales of billions of years, and past encounters between the two may have triggered bursts of star formation in Triangulum that remain visible today. More significantly for understanding the intergalactic medium, models of Triangulum's orbit suggest that it has passed through Andromeda's circumgalactic halo multiple times. Each passage would have stripped gas from Triangulum, leaving a trail of hydrogen in its wake. This gas would mix with Andromeda's own halo, creating disturbances and inhomogeneities in what might otherwise be a more symmetric structure. The space between galaxies is therefore not merely populated by static distributions of gas and dark matter. It is dynamic. It contains flows, wakes, and perturbations left by billions of years of galactic interactions. The local group is not a static arrangement of separate objects, but a complex evolving system in which every component influences every other component, and the medium between them carries the record of this long gravitational history. This dynamism will intensify dramatically as the Milky Way and Andromeda continue their approach. The closing velocity of 68 miles per second, constant for now, will accelerate as the galaxies draw closer and their mutual gravitational attraction strengthens. The approach is not linear but accelerating, a fall rather than a drift, governed by the same equations Newton wrote down in the 17th century to describe apples and orbits. Current models suggest that the first close passage will occur in approximately 4.5 billion years. The galaxies will not immediately merge but will instead swing past one another, their mutual gravity flinging them apart again before they fall back together. This dance will repeat several times over the following billion years, each passage stripping stars and gas from both participants, each encounter drawing energy from their relative motion, until orbital decay finally brings the cores together. The space between the galaxies, currently filled with diffuse halos and dark matter filaments, will become a war zone. Tidal tails of stars will be flung into orbits that carry them hundreds of thousands of light-years from either nucleus. Gas will be shocked and heated to temperatures at which it emits X-rays. Star formation will trigger in compressed regions where the colliding gas flows meet, creating new stellar populations in what was previously the darkest region of the local group. And somewhere in this chaos, the hypervelocity stars will continue their lonely journeys. Stars ejected from the Milky Way before the collision began will sail through the merger, unbound to either nucleus, continuing outward toward the truly intergalactic void beyond the local group. They will be among the last traces of the pre-merger galaxies, fossils of the separate spirals that once existed, travelling through a universe that will have long forgotten their origins. But we're getting ahead of the story. The merger lies billions of years in the future. and much remains to be understood about the present structure of the intergalactic medium before we can fully model its future transformation. The dark matter filament connecting the Milky Way to Andromeda, though inferred from theoretical considerations and indirect observations, remains one of the most challenging structures to characterize directly. Dark matter, by definition, does not interact with electromagnetic radiation in any detectable way. It does not emit light. It does not absorb light. It does not scatter light. The only tool available for mapping its distribution is gravity itself. Gravitational lensing provides the most powerful technique. When light from a distant source passes through a region containing significant mass, the gravitational curvature of space bends the light's path. This bending depends on the total mass present, whether that mass is visible or dark. By carefully measuring the distorted shapes of background galaxies, astronomers can reconstruct the mass distribution of intervening structures, including the invisible dark matter halos and filaments. For the filament between the Milky Way and Andromeda, lensing studies are extremely challenging. The background sources must be far more distant than the local group, and the signal is weak because the filament density, while enhanced above the cosmic average, remains extremely low in absolute terms. Current observations have not directly detected the local group filament, though they have detected similar filaments connecting more distant galaxy pairs at higher significance. The indirect evidence, however, is compelling. The satellites of both galaxies, the small dwarf systems orbiting the Milky Way and Andromeda, are not distributed randomly. They show a tendency to align in planes or streams that may reflect the underlying dark matter structure. The so-called plane of satellites around the Milky Way, a flat distribution that includes the large and small Magellanic Clouds, may represent dwarf galaxies accreting along the dark matter filament that connects us to the broader cosmic web. This alignment suggests that the void between galaxies is not merely a gap to be crossed, but a channel to be followed. Material falling into the local group from the surrounding universe preferentially flows along the filaments, guided by the gravitational ridges toward the nodes where major galaxies reside. The space between the Milky Way and Andromeda is therefore not disconnected from the space beyond the local group. It is continuous with the cosmic web, a local segment of a structure that extends across the entire observable universe. The recognition that the intergalactic medium possesses structure at all scales represents one of the great triumphs of modern cosmology. In the early 20th century, when Edwin Hubble first demonstrated that spiral nebulae were actually distant galaxies comparable to our own, the space between them was assumed to be perfectly empty, a true vacuum separating island universes. This assumption persisted for decades, not because evidence supported it, but because no evidence contradicted it. The transition from assumed emptiness to known structure has been gradual, driven by incremental improvements in observational capability. Each new instrument generation reveals additional complexity in regions previously dismissed as blank. The Lyman Alpha Forest revealed the pervasive presence of intergalactic hydrogen. X-ray satellites detected the hot halos surrounding galaxies. Radio interferometers mapped the distribution of neutral hydrogen in the circumgalactic medium. And gravitational lensing surveys began to reveal the dark matter architecture underlying it all. The pattern suggests a profound principle. Wherever we look with sufficient sensitivity, we find structure. The universe appears to abhor uniform emptiness. Even the most rarefied regions, the vast voids between galaxy clusters, where fewer than one atom per 10 cubic meters can be found, possess subtle density variations that trace the residual architecture of cosmic evolution. The space between the Milky Way and Andromeda, far from being a void between voids, is one of the denser regions of the intergalactic medium precisely because it lies between two massive galaxies. The gravitational influence of these two systems has attracted additional matter over billions of years, drawing hydrogen and dark matter inward from the surrounding cosmic web, and trapping it within the local group potential well. This material will not remain stationary. The collision between the galaxies will compress, shock, and redistribute it. Much of it will ultimately fall toward the merged galactic centre, feeding the combined supermassive black hole that will form when the nuclei of the Milky Way and Andromeda coalesce. Some will be flung outward by the violence of the interaction, escaping the merged system entirely and drifting into the true intergalactic void beyond. But that transformation lies in the deep future. For now, the space between the galaxies continues its patient existence, occupied by structures too faint for most observations to detect, too vast for human minds to intuitively grasp, and too slow-changing for any single human lifetime to perceive in motion. The hydrogen halos breathe outward and inward on timescales of hundreds of millions of years, responding to the rhythm of stellar feedback in their parent galaxies. The dark matter filament stretches and thins imperceptibly as the cosmic expansion pulls on regions beyond the local group, while the gravitational contraction draws the bound systems closer. The hypervelocity stars sail onward through darkness that will outlast their fusion cores, travelling paths that began in violence and will end in cold isolation. The void is not empty. It is merely patient, and its patience will end in fire. But the fire itself, the eventual collision and merger, represents only one chapter in the longer story of what fills the space between galaxies. Before we can understand the transformation, we must first understand the structures that will be transformed. We must examine the hydrogen halos in greater detail, tracing their temperature gradients and chemical compositions. We must probe the dark matter filament with every tool gravitational physics provides. We must follow the trajectories of hypervelocity stars and ask what their journeys reveal about the dynamics of galactic centers. The space that appears empty holds answers to questions about how galaxies form, how they grow, how they feed their ongoing star formation, and how they will eventually die. It is a laboratory of cosmic evolution, stretching across 2.5 million light-years, and we have only begun to learn how to read its contents. What fills this laboratory is neither nothing nor chaos. It is architecture. It is flow. It is the visible record of gravitational history, written in the distribution of matter across scales that dwarf every human reference frame. The void between the Milky Way and Andromeda is not a gap in the universe's fabric. It is part of the weave, as structured and significant as the galaxies themselves, and the collision that approaches will prove it. When these regions of diffuse gas and invisible scaffolding finally slam together at velocities measured in hundreds of kilometers per second, when the slow gravitational collapse that has been progressing for billions of years finally culminates in a violent reunion, the energy released will illuminate the darkness. The void will announce itself in X-rays and shock waves, and the sudden ignition of new stars born from compressed gas. But for now, in this present moment of cosmic history, the space between galaxies maintains its deceptive appearance of emptiness. The instruments capable of revealing its true contents remain expensive and oversubscribed, their observation time allocated in precious hours rather than the continuous campaigns the subject deserves. The diffuse hydrogen emits too faintly. The dark matter refuses to emit at all. The hypervelocity stars are too few and too distant to track in detail. We stand at the beginning of understanding. The void has only recently surrendered its first secrets, and those secrets suggest that far more remains hidden. The next generation of telescopes, the space-based ultraviolet observatories and the enormous ground-based radio interferometers under construction around the world, will reveal layers of structure currently invisible to us. What they find will almost certainly surprise us. Every improvement in observational capability has revealed unexpected complexity in regions previously assumed to be simple. The void between the Milky Way and Andromeda may yet contain structures no theorist has predicted, populations of matter or energy that current models fail to anticipate. But even within our current understanding, the picture that has emerged deserves contemplation. The space that most imagine as emptiness is already known to contain the overlapping hydrogen atmospheres of two great galaxies, the invisible gravitational scaffolding of dark matter that shapes the motion of everything within its reach, and the occasional refugee star travelling between worlds on journeys that will outlast the stars themselves. This is not nothing. This is a universe that fills every volume it can reach, that structures every scale it inhabits, that refuses the simplicity of emptiness in favour of endless, subtle complexity. The void is not empty, it is simply dark, and darkness is not absence. Darkness is merely what remains when we lack the instruments to see what is truly there. The hydrogen that fills the gulf between galaxies exists in states that challenge intuition about what it means for matter to be present at all. When we speak of the circumgalactic medium, the gaseous halos that extend far beyond the visible disks of spiral galaxies, we speak of densities so low that laboratory vacuums on Earth would seem crowded by comparison. The most rarefied reaches of the Milky Way's halo contain roughly 1 atom per cubic metre. To appreciate this emptiness, consider that the air you breathe right now contains approximately 25 trillion molecules in every cubic metre. The ratio between these two densities spans 25 orders of magnitude. If you were to somehow condense a cubic kilometre of circumgalactic gas into a volume small enough to hold in your hand, you might collect enough atoms to fog a mirror for a fraction of a second. Yet this near-nothingness represents, in aggregate, a mass comparable to the stellar content of the galaxy itself. The Milky Way contains somewhere between 100 billion and 400 billion stars, their combined mass totalling roughly 1 trillion solar masses when we include stellar remnants, brown dwarfs, and the other dim objects that populate our galaxy. The circumgalactic medium surrounding this stellar population contains an estimated 1 trillion solar masses of its own, spread across a volume so enormous that the individual atoms rarely encounter one another. A hydrogen atom in the outer reaches of the Milky Way's halo might travel for 1,000 years at thermal velocities before colliding with another particle. Its existence is one of profound isolation, drifting through darkness with only the faintest gravitational whisper from the distant galactic centre to guide its motion. This isolation does not imply uniformity. The circumgalactic medium reveals itself, when observed with sufficient sensitivity, as a landscape of density variations, temperature gradients, and chemical inhomogeneities that record the history of the galaxy's formation and evolution. The techniques required to map this landscape push the limits of modern observational astronomy, demanding either the light of a background quasar to illuminate the foreground gas through absorption, or the patient accumulation of faint emission photons over hours of telescope time. Both approaches have contributed to our emerging picture of the halo's structure, and both have revealed that the hydrogen atmosphere of a galaxy is far from the smooth, featureless envelope that simplified models once assumed. The temperature structure alone spans several orders of magnitude. Near the galaxy's disk, where stellar winds and supernova explosions continuously heat the gas, temperatures can exceed 1 million degrees Kelvin. This coronal gas, analogous to the superheated corona that surrounds our own Sun, produces X-ray emission detectable by space-based observatories. The Chandra X-ray Observatory and the XMM Newton telescope have mapped this hot component for both the Milky Way and Andromeda, revealing extended halos of superheated plasma that glow faintly across the electromagnetic spectrum. The energy contained in this coronal gas represents the accumulated output of billions of stellar explosions over the lifetime of the galaxy. Every supernova that has detonated in the Milky Way over the past 12 billion years has contributed thermal energy to this reservoir, heating the surrounding medium and driving turbulent motions that persist for millions of years after the explosion itself has faded. Further from the disk, the temperatures gradually decrease, though they remain far hotter than the frigid 3-degree background of intergalactic space. At distances of 50 kiloparsecs from the galactic centre, roughly 160,000 light-years, this circumgalactic medium maintains temperatures in the range of hundreds of thousands of degrees. This is the warm-hot component, existing in a temperature regime where hydrogen is partially ionized but not yet hot enough to produce detectable X-ray emission. Observing this phase requires ultraviolet spectroscopy, the detection of absorption lines from highly ionized oxygen, nitrogen, and carbon that trace the presence of the underlying hydrogen. The cosmic origin spectrograph aboard the Hubble Space Telescope has proven particularly valuable for these observations, using distant quasars as cosmic flashlights that illuminate the tenuous gas along the line of sight. Beyond the warm-hot phase lies cooler material, hydrogen at temperatures of merely tens of thousands of degrees, producing absorption in the ultraviolet Lyman alpha line that serves as the primary tracer of neutral and mildly ionized hydrogen throughout the universe. This cooler gas forms cloud-like structures embedded within the hotter medium, condensations where local density enhancements have allowed the material to radiate away its thermal energy and settle toward temperatures where molecules might eventually form. These clouds represent the raw material from which future star formation might draw, reservoirs of relatively dense gas suspended within the tenuous corona, slowly spiraling inward along trajectories that may span hundreds of millions of years. The motion of circumgalactic gas is neither static nor simple. Observations reveal both infall and outflow operating simultaneously, a complex circulatory system that connects the intergalactic medium, the galactic halo, and the star-forming disk through pathways of gas flow that have shaped the evolution of galaxies across cosmic time. The outflows originate from the disk itself, driven by the combined pressure of supernova explosions, stellar winds, and radiation from young massive stars. When a burst of star formation ignites in a spiral arm, the subsequent deaths of short-lived massive stars can inject enough energy to blow a chimney through the surrounding interstellar medium, venting hot gas into the halo at velocities of hundreds of kilometers per second. These galactic fountains, as they are sometimes called, carry enriched material away from the disk, gas that has been processed through stellar interiors and now contains the heavy elements forged by nuclear fusion and explosive nucleosynthesis. The fate of this ejected material varies. Some fraction achieves escape velocity, departing the galaxy entirely and enriching the intergalactic medium with metals that will eventually accumulate in other galaxies or remain forever dispersed in cosmic voids. But much of the outflowing gas lacks sufficient velocity to escape the gravitational potential of the halo. It rises, cools, and eventually falls back toward the disk in a cycle of circulation that can span tens of millions of years per orbit. This recycled material returns to the star-forming regions, carrying the chemical fingerprints of previous stellar generations, gradually increasing the metallicity of the interstellar medium over cosmic time. Simultaneously, fresh gas falls inward from the intergalactic medium itself. This cosmological accretion represents the continuation of the process that built the galaxy in the first place, the gradual accumulation of pristine hydrogen that has never been processed through stellar interiors. The rate of this infall determines in part how long a galaxy can continue forming stars. The Milky Way currently converts gas into stars at a rate of approximately 2 solar masses per year, a seemingly modest figure that nevertheless implies a need for continuous replenishment. Without infall from the circumgalactic medium, the galaxy's reservoir of star-forming gas would be depleted within a few billion years, bringing the epoch of stellar birth to an end. The fact that star formation has continued at roughly constant rates for billions of years implies that accretion has balanced consumption, that the circumgalactic medium serves as a fuel tank whose contents flow steadily inward to power the galaxy's ongoing activity. Mapping these flows requires distinguishing inward-moving gas from outward-moving gas, a task that depends on precise velocity measurements toward multiple lines of sight. The spectral signatures of circumgalactic absorption reveal not only the presence of gas, but also its motion relative to the galaxy. Blue-shifted absorption indicates material moving toward the observer, which for gas positioned between Earth and a background quasar implies motion toward the galactic disk. Red-shifted absorption indicates the opposite, material receding from the disk, potentially representing galactic winds or fountain flows in their ascending phase. By combining observations toward dozens of background quasars positioned at different locations relative to the galaxy's disk and rotation axis, astronomers have begun to construct three-dimensional maps of halo dynamics that reveal the complexity of galactic breathing. The Milky Way's halo shows clear signatures of both processes. The Magellanic Stream, a vast ribbon of hydrogen stretching across more than 100 degrees of sky, represents material being stripped from the large and small Magellanic Clouds, our galaxy's most prominent satellite galaxies, as they orbit through the circumgalactic medium. This stream demonstrates that the halo is not merely passive. Its density, though incredibly low, is sufficient to exert ram pressure on objects moving through it, much as Earth's atmosphere exerts drag on spacecraft re-entering from orbit. The Magellanic Clouds are losing mass to this interaction, gas being peeled away from their outskirts and stretched into a trailing wake that feeds into the Milky Way's own reservoir. This is galactic feeding in action, visible to radio telescopes as a continuous arc of neutral hydrogen, connecting the satellite galaxies to their massive host. Similar processes may be operating in Andromeda, though our external perspective makes different features visible. We cannot easily see streams of gas falling into our own galaxy's disk because we are embedded within the disk itself, observing outward through confused foreground emission. But Andromeda presents its circumgalactic medium in projection against the relatively clean background of distant extragalactic space. Observations with the Hubble Space Telescope's Cosmic Origin spectrograph, part of the Omega survey that mapped absorption toward 43 background quasars positioned behind Andromeda's halo, revealed that the circumgalactic medium extends far beyond the visible galaxy. Significant absorption was detected at projected distances exceeding 500 kiloparsecs from Andromeda's center, roughly 1.6 million light-years, meaning that the gaseous envelope surrounding our neighbour extends more than halfway toward our own galaxy. The implications are striking. If both galaxies possess halos of comparable extent, and the evidence suggests they do, then these halos are not merely approaching each other, they are already touching. The diffuse outer reaches of the Milky Way's circumgalactic medium have likely already begun interacting with the corresponding regions of Andromeda's hydrogen atmosphere, though the densities involved are so low that the interaction produces no dramatic observational signatures. There is no shock front, no sudden compression, no detectable heating at the current stage. The overlap is gentle, a gradual interpenetration of two impossibly thin gases whose particles rarely collide even when sharing the same volume of space. But this interaction will intensify as the galaxies draw closer, as the regions of overlap extend to higher density portions of each halo, and eventually as the halos themselves begin to compress under the momentum of the approach. Understanding the chemistry of circumgalactic gas adds another layer to this already complex picture. The hydrogen that dominates these halos is accompanied by trace amounts of heavier elements, metals in the astronomical sense of any element heavier than helium, that record the history of stellar processing across the galaxy's lifetime. These metals arrive in the circumgalactic medium through the galactic winds that carry enriched material away from the disk. Their abundances vary with distance from the galactic centre, with position relative to the disk's plane, and with the specific absorption systems being probed. Near the disk, where outflows are strongest and most recent, metallicities can approach a significant fraction of solar values. Further out, where pristine intergalactic gas mixes with recycled fountain material, the abundances drop to a few % of solar or even less. The distribution of metals within the circumgalactic medium traces the history of galactic activity with remarkable fidelity. Regions enriched by recent supernova-driven outflows show enhanced abundances of oxygen, silicon, and iron, the products of massive star evolution and Type Ia supernovae. Regions dominated by older enrichment events, outflows that occurred billions of years in the past and have since mixed throughout the halo, show more uniform but lower abundances. By mapping these chemical variations, astronomers can reconstruct the intensity and duration of star formation episodes, the timing of major merger events that might have triggered starbursts, and the geometry of outflows over cosmic time. The nitrogen-to-oxygen ratio proves particularly diagnostic. Nitrogen production in stars differs from oxygen production in ways that depend on the mass and metallicity of the stellar population. Primary nitrogen forms directly from hydrogen and helium in massive stars, while secondary nitrogen requires pre-existing carbon and oxygen as seed nuclei, forming preferentially in lower mass stars with longer lifetimes. The relative abundances of these elements in circumgalactic gas therefore carry information about the age of the stellar populations that produced them, allowing astronomers to date enrichment events that occurred billions of years before the present. Carbon plays its own revealing role. As one of the most abundant metals produced by stellar nucleosynthesis, carbon produces strong absorption features in ultraviolet spectra, particularly the triply ionized carbon line at 1548 angstroms, that serves as a standard tracer of the warm ionized medium. The distribution of carbon absorption around galaxies reveals the extent to which outflows have spread enriched material through the halo, sometimes reaching remarkably large distances. Detections of carbon absorption at projected separations exceeding 300 kiloparsecs from galaxy centers suggest that galactic winds can transport processed material far beyond what simple models predict, seeding the intergalactic medium with metals that will eventually be incorporated into future generations of galaxies. The interaction between the Milky Way's and Andromeda's circumgalactic media will eventually mix these chemical reservoirs. Gas enriched by different stellar populations in different galaxies will combine, their chemical signatures blending into a new composition that reflects the merged history of both systems. But mixing at these densities is an extraordinarily slow process. Without frequent collisions between particles to homogenize velocities and compositions, the gas from each progenitor galaxy will retain distinct kinematic and chemical signatures for hundreds of millions of years after the merger begins. The eventual combined circumgalactic medium of Milkomeda, as the merged galaxy is sometimes called, will bear the scars of its origin as two separate systems for billions of years, perhaps forever in the regions where densities remain too low for effective mixing to occur. The temperature evolution of circumgalactic gas during the merger will produce observable consequences even before the galaxy's stellar components begin their interaction. As the halos compress under their mutual approach, the kinetic energy of bulk motion will convert to thermal energy through shocks and turbulent dissipation. The warm-hot phase, currently difficult to detect because its temperature falls in an awkward range between X-ray and ultraviolet sensitivity, may heat to the point of X-ray visibility, creating an extended glow that envelops both approaching galaxies. Simulations of galaxy collisions consistently predict enhanced X-ray emission during the pre-collision phase, a signature of circumgalactic heating that can precede the first passage of the stellar cores by hundreds of millions of years. For the Milky Way Andromeda system, this heating phase lies far in the future, but it represents a transition point where the merger becomes dramatic rather than subtle. The current gentle interpenetration of outer halo gas produces no detectable signature because the velocities involved are modest and the densities are negligible. But as the galaxies draw within a few hundred kiloparsecs of each other, the velocities will increase toward the hundreds of kilometers per second that characterize the final approach. At these speeds, even the tenuous circumgalactic medium will shock and heat, its signature finally rising above the detection threshold of X-ray observatories. The role of magnetic fields in circumgalactic gas adds a dimension often overlooked in discussions of galactic halos. Magnetic fields pervade the interstellar medium of spiral galaxies, organized into patterns that follow the spiral arms and extend into the halo through the same processes that drive galactic winds. The strength of these fields, typically a few microgauss in the disk and declining to fractions of a microgauss in the halo, seems negligible by terrestrial standards. A refrigerator magnet exceeds the circumgalactic field strength by a factor of roughly 100 million. Yet over the vast scales involved, even these weak fields influence gas dynamics in measurable ways. Magnetic pressure contributes to the support of gas against gravitational collapse. Cosmic rays, charged particles accelerated to relativistic velocities by supernova remnants and other energetic phenomena, become trapped along magnetic field lines, unable to cross field boundaries as freely as thermal particles. This trapping creates an effective pressure that supplements thermal pressure in supporting the gas against gravity. In some regions, cosmic ray pressure may even dominate over thermal pressure, fundamentally altering the equilibrium structure of the circumgalactic medium. The role of this non-thermal component remains an active area of research, with simulations increasingly incorporating magnetohydrodynamics and cosmic ray physics to capture effects that simpler hydrodynamic models miss. The magnetic fields threading the circumgalactic medium will also interact during the merger. Unlike the hydrogen gas, which mixes only gradually, magnetic fields can reconnect, events where field lines from different sources merge and release stored magnetic energy in explosive bursts. Magnetic reconnection may accelerate particles to high energies, contribute to heating the surrounding gas, and generate phenomena analogous to the solar flares that erupt on our own sun. The scales involved dwarf anything in the solar system, reconnection events potentially releasing energies equivalent to billions of solar flares occurring simultaneously across regions spanning thousands of light years. These considerations reveal the circumgalactic medium as a system of extraordinary complexity, a multi-phase environment where hot and cool gas coexist, where inflows and outflows compete, where chemistry records history and magnetic fields shape dynamics. The space that appears empty to casual observation emerges under careful scrutiny as a richly structured domain whose properties influence the evolution of the galaxies it surrounds. The 2.5 million light-years between the Milky Way and Andromeda contain not void but atmosphere, not absence, but presence at densities that test our ability to detect anything at all. And beneath this gaseous complexity lies the gravitational infrastructure that shapes everything. The dark matter that comprises 5 times the mass of all ordinary matter in the universe does not float freely through space. It clusters, it flows, it builds scaffolding on which baryonic matter accumulates. The filament connecting our galaxy to Andromeda represents one thread in the cosmic web, a structure whose existence was predicted by theory before observations confirmed it, and whose properties continue to challenge our understanding of gravity on the larger scales. The geometry of this filament departs from the simple expectations that might arise from considering only 2 isolated galaxies. If the Milky Way and Andromeda existed in perfect isolation, with no other mass influencing their dynamics, the dark matter distribution between them would reflect only their mutual gravitational attraction. Matter would flow along the line connecting their centres, creating an axially symmetric bridge that thickened gradually toward each endpoint. But the local group contains more than two major galaxies. The dozens of satellite galaxies, the dark matter halos of those satellites, and the cosmic structures beyond the local group all contribute to the gravitational environment in ways that break simple symmetry. The result is a filament with structure, a bridge that varies in thickness and density along its length, that curves subtly in response to external gravitational influences, and that branches where smaller concentrations of matter interrupt its geometry. Simulations of local group formation consistently produce such structures, dark matter filaments that connect major halos while bearing the imprint of the larger cosmic web in which the group formed. The observational challenge lies in detecting this structure, in measuring the gravitational influence of matter that neither emits nor absorbs light through any known process. Gravitational lensing provides one approach. Light from background galaxies passing through the local group experiences deflection proportional to the mass encountered along the path. By measuring the tiny distortions in galaxy shapes induced by this lensing, astronomers can infer the distribution of mass regardless of whether that mass produces any detectable radiation. This technique has revolutionized the study of dark matter on cluster scales, where the mass concentrations are enormous and the lensing signatures are strong. But applying gravitational lensing to the relatively diffuse filament between the Milky Way and Andromeda requires extraordinary precision. The expected signal is smaller than the systematic uncertainties that affect current measurements, buried beneath noise from intrinsic galaxy shapes, observational errors, and confusion from foreground structures. Progress will require the next generation of space telescopes, instruments designed with gravitational lensing as a primary science goal, equipped with the wide fields of view and stable point spread functions necessary to measure galaxy shapes with the precision the measurement demands. The Euclid mission, launched in 2023, and the Nancy Grace Roman Space Telescope, scheduled for later this decade, will push these boundaries forward. Whether they will achieve the sensitivity needed to directly map the local group filament remains uncertain, but each improvement brings the detection closer to feasibility. Another approach exploits the relative motions of galaxies within and around the local group, the velocities of satellite galaxies, the peculiar motions of galaxies just beyond the local group boundary, and the subtle reflex motions of the Milky Way and Andromeda themselves all encode information about the underlying mass distribution. By building dynamical models that attempt to reproduce these observed velocities, astronomers can constrain the total mass of the local group and its spatial distribution. These models consistently indicate that the dark matter extends far beyond the visible components of each galaxy, that the halos overlap significantly in the region between them, and that the total mass of the system exceeds what would be inferred from the luminous matter by a factor of roughly 10. The filament is there, the models insist. The challenge is seeing it directly rather than inferring its presence from gravitational choreography. The composition of this filamentary dark matter remains one of the deepest mysteries in modern physics. For decades, the leading candidates have been weakly interacting massive particles, hypothetical particles left over from the early universe that interact with ordinary matter only through gravity and perhaps the weak nuclear force. Experiments buried deep underground have searched for the rare collisions between these particles and atomic nuclei that might occur when Earth moves through the galactic dark matter halo. Despite decades of increasingly sensitive searches, no definitive detection has emerged. The parameter space where WIMPs might hide has shrunk dramatically, though it has not been entirely eliminated. Alternative candidates have gained attention. Axions, extremely light particles originally proposed to solve a different puzzle in particle physics, could constitute the dark matter if they exist in sufficient abundance. Primordial black holes, formed not from stellar collapse but from density fluctuations in the early universe, remain a possibility in certain mass ranges. Sterile neutrinos, exotic particles that interact even more weakly than ordinary neutrinos, could explain the dark matter while potentially leaving subtle signatures in X-ray observations. Each candidate would have different implications for the structure of the filament between our galaxies. If dark matter consists of relatively heavy particles that move slowly compared to the speed of light, the filament would exhibit small-scale structure, clumps and subhalos that formed through gravitational collapse in the early universe. These substructures would pepper the bridge between the Milky Way and Andromeda, dark matter concentrations ranging from the mass of small dwarf galaxies down to perhaps the mass of asteroids. If instead dark matter consists of extremely light particles behaving more like waves than particles, the filament would appear smoother on small scales, the quantum pressure of such fuzzy dark matter preventing the formation of structures below a characteristic size. The difference matters not only for understanding dark matter itself, but for predicting what happens when the galaxies collide. Substructure in the dark matter would create a more turbulent merger, with gravitational interactions between small halos adding complexity to the collision dynamics. Smoother dark matter would produce a more orderly encounter, the halos passing through each other like interpenetrating clouds. Current observations cannot definitively distinguish between these possibilities at the scales relevant to the local group filament. But the mere existence of the filament, regardless of its fine structure, transforms our understanding of the space between galaxies. The dark matter does not simply fill the halos of individual galaxies and then stop. It extends outward, thinning but never vanishing entirely, until it merges with the dark matter extending from neighbouring galaxies. The boundary between one halo and another becomes arbitrary, a surface drawn for convenience rather than a physical discontinuity. In this sense, the Milky Way and Andromeda have been connected since their formation, their dark matter distributions overlapping from the beginning, their gravitational fates intertwined across cosmic time. The filament is not a bridge built between two separate structures. It is the continuous medium in which both structures formed and in which both continue to evolve. The geometry of this cosmic web architecture deserves contemplation. When we speak of the filament connecting our galaxy to Andromeda, we describe one strand in a vastly larger structure that pervades the observable universe. The cosmic web emerged from tiny density fluctuations in the early universe, irregularities imprinted during inflation, and amplified by gravity over billions of years. Matter flowed from underdense regions into overdense ones, emptying the voids and building the walls, filaments, and nodes that constitute the web. The local group sits at the intersection of several filaments, connected not only to Andromeda, but to the broader cosmic structure beyond. The Virgo cluster lies roughly 50 million light-years away, a massive concentration of galaxies whose gravitational pull influences the motions of everything in its neighbourhood. The local group moves toward Virgo at hundreds of kilometers per second, drawn by this distant mass concentration. But Virgo itself moves toward still larger structures, and those structures toward others, in a cascade of gravitational flows that ultimately traces back to the primordial density field. The filament between the Milky Way and Andromeda thus exists within a hierarchy of structure. It connects two major galaxies within the local group. The local group connects to the Virgo supercluster through larger filaments. The Virgo supercluster forms part of the Laniakea supercluster, a vast structure containing hundreds of thousands of galaxies whose motions flow toward a gravitational focus known as the Great Attractor. Understanding the local group filament requires placing it within this hierarchy, recognizing that the forces shaping the space between our galaxy and Andromeda extend to cosmological scales and timescales. This hierarchical context matters for another reason. The local group is falling inward, yes, but it also participates in the expansion of the universe at larger scales. The Milky Way and Andromeda are approaching each other because their mutual gravitational attraction has overcome the expansion that would otherwise carry them apart. But galaxies more distant than a few million light-years continue receding, carried by the expansion that dominates at larger scales. The boundary between the gravitationally bound local group and the expanding universe beyond defines a sphere of influence, a region where gravity has won its local battle against cosmic expansion. The diameter of this sphere measures perhaps 10 million light-years, encompassing the local group and some of its immediate neighbours, while the universe beyond continues to expand away. Within this sphere, the dark matter filament participates in the ongoing collapse. Matter flows along the filament toward the centre of mass of the local group, feeding the growth of both major galaxies even as they spiral toward merger. The flow is slow by human standards but relentless by cosmic ones, a gradual accumulation that has continued for billions of years and will continue until the merger scrambles the ordered flow into more chaotic motions. The filament is not static. It is a conduit, a highway along which matter travels from the cosmic web into the galaxies that constitute the nodes of that web. And now we must confront what truly inhabits this filament. What physical objects exist in the space between galaxies beyond the diffuse gas and invisible dark matter? For the gap between the Milky Way and Andromeda contains stars. Not many, not compared to the hundreds of billions that populate each galaxy proper, but stars nonetheless. Their existence challenges the intuition that interstellar space ends at some definable boundary and that the space between galaxies is genuinely stellar-free. The reality is more nuanced, more fascinating, and ultimately more revealing about the violent processes that shape galactic evolution. Hypervelocity stars represent the most dramatic population. These are stars ejected from galaxies at speeds exceeding the escape velocity, stars on trajectories that will carry them into intergalactic space never to return. The discovery of hypervelocity stars began in 2005, when a survey of stellar velocities in the Milky Way's halo revealed a star moving at over 700 kilometers per second relative to the galactic center. This velocity was extraordinary. The escape velocity from the Milky Way at the star's position was roughly 500 kilometers per second. The star was not bound to the galaxy. It was leaving, permanently, on a trajectory that would carry it into the void between galaxies. The mechanism behind such extreme velocities became clear through theoretical work that predated the discovery. In 1988, Jack Hills had predicted that close encounters between binary star systems and the supermassive black hole at the centre of a galaxy could produce just such high-velocity escapees. The scenario requires a binary star system to wander close to the central black hole, close enough that tidal forces from the black hole's immense gravity rip the binary apart. One star falls into a tight orbit around the black hole, potentially spiralling inward to eventual destruction. The other star, through conservation of energy and momentum in the three-body interaction, gets flung outward at enormous speed. Hills calculated that the ejection velocities could reach thousands of kilometers per second in extreme cases, more than sufficient to escape any galaxy. The Hills mechanism has proven to be the dominant source of hypervelocity stars, though not the only one. Supernova explosions in binary systems can also produce high-velocity runaways when one star explodes and the other, suddenly released from the gravitational bond, flies off at whatever velocity it had in its orbital motion. Dynamical interactions in dense stellar clusters can similarly eject stars at high speeds. But the most extreme velocities, the true hypervelocity escapees that will travel millions of light-years from their origin, come predominantly from encounters with supermassive black holes. The Milky Way harbours such a black hole, Sagittarius A, with a mass of roughly 4 million times that of the Sun. Andromeda's central black hole is even larger, perhaps 100 million solar masses or more. Both galaxies have been ejecting hypervelocity stars throughout their histories, and the space between them contains the accumulated population of these ejections. Estimating the number requires modelling the rate of binary star encounters with each central black hole, the distribution of ejection velocities, and the time over which these ejections have occurred. The calculations suggest that each major galaxy ejects roughly one hypervelocity star per 100,000 years on average. Over the 10 billion years since both galaxies reached something like their current configurations, this rate implies tens of thousands of hypervelocity stars ejected by each galaxy. Most of these stars remain within the dark matter halos of their parent galaxies, their velocities high but not quite sufficient to escape entirely. They orbit through the halo on highly eccentric trajectories, reaching distances of hundreds of thousands of light-years from the galactic centre before falling back. But the fastest among them, the stars ejected at the extreme tail of the velocity distribution, do escape. They cross the boundary of the dark matter halo and enter true intergalactic space, their motion now influenced only by the gravitational pull of the entire local group rather than their parent galaxy alone. The journey of a hypervelocity star across the space between galaxies unfolds over timescales that dwarf human comprehension. Consider a star ejected from the centre of the Milky Way at 1,000 kilometers per second, a velocity at the upper range of what the Hills mechanism can produce. At this speed, the star covers roughly 30 billion kilometers per year, approximately 3 light-years per million years. To traverse the 2.5 million light-year gap to Andromeda would require over 800 million years. The star would cross the intergalactic medium as a solitary beacon, its light shining into the void for hundreds of millions of years before reaching the gravitational sphere of influence of its destination galaxy. But the star itself would not survive the journey unchanged. The most massive stars, the brilliant blue giants that outshine the Sun by factors of thousands, burn through their nuclear fuel in mere millions of years. A hypervelocity star of such luminosity would exhaust its core hydrogen long before completing a fraction of the journey, swelling into a red giant, potentially exploding as a supernova and leaving behind only a compact remnant. The hypervelocity stars that actually complete intergalactic crossings must be lower mass stars, the orange and red dwarfs that burn their fuel slowly enough to persist for billions of years. These stars are intrinsically faint, their luminosity perhaps a tenth or 100th that of the Sun, making them extraordinarily difficult to detect at intergalactic distances. The few hypervelocity stars discovered so far are biased toward higher masses and higher luminosities, the stars bright enough to appear in spectroscopic surveys despite their extreme distances. The true population of hypervelocity stars in intergalactic space is certainly larger than the observed population, dominated by the faint red dwarfs that escape detection with current technology. Some fraction of these low-mass escapees have completed their journeys across the local group void, transitioning from the gravitational domain of one galaxy to another. A star ejected from the Milky Way's centre 800 million years ago, at sufficient velocity would now be approaching Andromeda's halo, its trajectory bending as Andromeda's gravity begins to dominate. It would enter Andromeda not as a native but as an immigrant, its chemical composition bearing the signature of its Milky Way origin, its stellar age recording its birthplace in the spiral arms of a different galaxy. The reverse occurs as well. Andromeda has ejected its own hypervelocity stars, some of which have crossed the void in the opposite direction. The Milky Way's outer halo may contain stars born in Andromeda, stellar immigrants that arrived billions of years ago and now orbit through our galaxy's outskirts. Distinguishing such stars from native Milky Way stars would require detailed chemical analysis, comparing the elemental abundances in their atmospheres to the distinct chemical enrichment histories of each galaxy. This remains a task for future spectroscopic surveys, instruments capable of measuring the chemistry of faint halo stars with precision sufficient to identify their origin. Beyond the hypervelocity stars ejected by black hole encounters, the intergalactic medium contains another stellar population, stars stripped from their parent galaxies through tidal interactions. When a satellite galaxy falls into the halo of a larger galaxy, tidal forces stretch and distort it, pulling stars from its outer regions into streams that trace the orbital path. This process of tidal stripping has been observed around both the Milky Way and Andromeda, with numerous stellar streams identified in the halos of each galaxy. But the stripping does not stop at the halo boundary. In some cases, the tidal debris spreads into true intergalactic space, forming bridges of stars between galaxies that have interacted. The Magellanic Clouds provide a spectacular example. These two satellite galaxies of the Milky Way, visible to the naked eye from the southern hemisphere, have been stretched by tidal forces during their orbital passages around our galaxy. The Magellanic Stream, a vast ribbon of hydrogen gas extending over 200 degrees across the sky, traces the orbital debris of this interaction. And mixed within the gas are stars, stripped from the clouds and scattered along the stream. Some of these stars now occupy positions that place them outside the traditional boundary of the Milky Way's halo, inhabiting the intermediate space between our galaxy and the larger cosmic environment. The same process has occurred throughout the local group. Andromeda's halo shows extensive evidence of past accretion events, with stellar streams and shells recording the destruction of smaller galaxies over billions of years. Some of this debris extends well beyond Andromeda's nominal halo radius, reaching into the space between Andromeda and its neighbours. The dwarf galaxy, MF32, a compact satellite of Andromeda, may itself be the stripped remnant of a larger galaxy that passed too close to Andromeda in the past, losing most of its outer stars to tidal forces. Those stripped stars now populate the space around Andromeda, contributing to the diffuse stellar light that fills the intergalactic medium. This diffuse light represents yet another component of the space between galaxies. Known as intracluster light in the context of galaxy clusters, or intrahalo light around individual galaxies, this glow arises from stars that belong to no single galaxy, but instead orbit freely through the gravitational potential of the larger structure. Measurements of intrahalo light around the Milky Way and Andromeda suggest that a few % of all stellar mass in the local group exists in this unbound or loosely bound population. These are not stars in the traditional sense of belonging to a galaxy. They are orphan stars, gravitationally bound to the local group as a whole, but not to any individual member. Detecting these stars directly is extremely challenging. Their surface density on the sky is extraordinarily low, perhaps 1 star per square degree at magnitudes accessible to current surveys. Identifying them requires distinguishing genuine intergalactic stars from the overwhelming foreground of Milky Way disk and halo stars, a task that demands precise distance measurements and proper motion data. The Gaia mission has provided such data for over 1 billion stars, enabling new searches for intergalactic populations. Initial results suggest that the transition between the Milky Way's halo and the intergalactic medium is gradual rather than sharp, with stellar density declining smoothly but never reaching exactly zero. The stars that populate the space between galaxies carry information about their origin. Their ages record when they were ejected or stripped. Their chemical compositions reveal the environments in which they formed. Their velocities and orbital parameters trace the gravitational interactions that place them in their current positions. Each hypervelocity escapee, each tidally stripped stream star, each orphaned halo wanderer represents a fossil record of dynamical processes that have shaped the local group over cosmic time. Reading that record requires surveys of extraordinary depth and precision, but the effort promises insights into galactic evolution that cannot be obtained by studying the galaxies themselves in isolation. The chemical story told by these intergalactic stars deserves particular attention. Stars form from gas, and the gas from which they form carries the elemental signatures of all the previous stellar generations that enriched it. A star born in the centre of a massive galaxy, where many generations of stars have lived and died and contributed their nucleosynthetic products to the interstellar medium, will have a different chemical composition than a star born in the sparse outskirts of a dwarf galaxy, where only a few generations of enrichment have occurred. Elements like iron, magnesium, and calcium accumulate in predictable ratios that depend on the star formation history and the mass of the host galaxy. By measuring these ratios in intergalactic stars, astronomers can infer not only which galaxy ejected them, but also from what region of that galaxy they originated and at what epoch they formed. The hypervelocity stars ejected from the centres of the Milky Way, and Andromeda would bear the chemical signatures of the nuclear star clusters surrounding each supermassive black hole. These are regions of extreme stellar density and intense star formation, where the chemical enrichment history has proceeded rapidly, and the resulting stellar compositions are distinctly enhanced in certain elements. A hypervelocity star with such a composition, found in the intergalactic medium between the galaxies, would provide unambiguous evidence of its origin in a close encounter with a supermassive black hole. Stars stripped from dwarf satellites would carry different signatures, compositions reflecting the truncated chemical evolution of small galaxies with low star formation rates and significant loss of enriched gas to galactic winds. The diversity of chemical patterns in the intergalactic stellar population would map the diversity of environments from which those stars were extracted, creating a chemical archaeology of local group assembly. And so we find that the space between the Milky Way and Andromeda contains genuine stellar inhabitants, not merely the diffuse gas and invisible dark matter that fill the apparent void. These stars are few, scattered across millions of light years at densities so low that their nearest neighbours lie thousands of light years distant. They shine in isolation, their light taking thousands of years to reach even other intergalactic stars. Each such star represents a world, potentially with planets, certainly with the nuclear furnace at its core producing light and heat as it has for billions of years. These are perhaps the loneliest places in the universe, stellar systems adrift in the void between galaxies, their night skies showing only the faint fuzzy patches of distant galaxies, rather than the glorious band of a galactic plane. The light of 1,000 billion stars fills the sky of a planet in a galactic disk, but an intergalactic world would see only darkness punctuated by the distant glow of island universes. Yet even these loneliest stars are not truly alone. They exist within a structure, a framework of matter and gravity that binds the local group together and ensures that its constituent pieces will not drift apart forever into the expanding cosmos. The space between the Milky Way and Andromeda is not merely a passive void through which a few ejected stars wander. It is an active participant in the gravitational drama that has been unfolding for billions of years, and will reach its climax in approximately 4.5 billion years more. The collision between our galaxy and Andromeda is not a future possibility. It is a present reality, a process already underway, one that began when the first atoms of hydrogen in the circumgalactic medium of each galaxy began to feel the gravitational influence of the other. To understand what will happen when these galaxies meet, we must first understand what it means for galaxies to collide. The word collision evokes images of violence, of solid objects smashing together, of debris and destruction. But galaxies are not solid objects. They are collections of stars separated by vast distances, embedded in halos of gas and dark matter that extend far beyond their visible boundaries. When two galaxies collide, their stars do not typically strike each other. The distances between stars are so enormous relative to stellar sizes that direct collisions are vanishingly improbable. If you scaled the Sun down to the size of a grain of sand, the nearest star would be another grain of sand 4 miles away. Even in the dense cores of galaxies, stellar collisions are rare events occurring over millions of years. In a galactic merger, stars pass by each other like gnats flying through intersecting swarms. What does collide is gravity. The gravitational field of each galaxy perturbs the orbits of stars in the other, reshaping both systems over hundreds of millions of years. Stars that followed orderly circular orbits around their galactic centres find themselves flung onto elongated ellipses, scattered into new trajectories, heated into chaotic motion. The elegant spiral arms and organised disk structures that characterise spiral galaxies like the Milky Way and Andromeda are fragile arrangements, maintained by the collective gravity of billions of stars moving in coordinated patterns. When another galaxy's gravity intrudes, those patterns are disrupted. Spiral arms unwind, disks warp and eventually merge into a single amorphous spheroid. The stately pinwheel shapes transform into the featureless elliptical blobs that dominate the population of large galaxies in dense environments. Gas behaves differently than stars in a galactic collision. Unlike stars, gas clouds can collide directly. When the diffuse hydrogen of one galaxy's circumgalactic medium encounters the diffuse hydrogen of another, the two cannot pass through each other. They ram together at relative velocities of hundreds of kilometers per second, compressing and heating and shocking the gas to temperatures of millions of degrees. This collision of gas produces consequences that the stellar collision does not. Compressed gas forms new stars. Heated gas emits X-rays. Shocked gas loses angular momentum and falls toward the centres of the merging galaxies, potentially feeding the supermassive black holes that lurk there. The Milky Way and Andromeda are already engaged in this process. Their circumgalactic halos, those vast envelopes of diffuse hydrogen, extending hundreds of thousands of light-years from each galactic centre, have already begun to overlap. The edge of the Milky Way's gaseous halo, as mapped by the absorption of background quasar light, extends roughly 600,000 light-years from the galactic centre. The edge of Andromeda's halo extends a similar distance. With 2.5 million light-years separating the two galactic centres, simple geometry suggests a gap of roughly 1.3 million light-years between the outer edges of the two halos. But halos are not sharp-edged spheres. They are fuzzy, diffuse structures whose density declines gradually with distance. The outermost wisps of each halo, the most tenuous reaches of the circumgalactic medium, almost certainly interpenetrate already. Atoms of hydrogen that spent billions of years orbiting the Milky Way are mixing with atoms that spent billions of years orbiting Andromeda. The merger has begun. The pace of this merger seems glacial by human standards, but is remarkably swift by cosmic ones. Andromeda is approaching the Milky Way at approximately 110 kilometers per second. This velocity sounds modest compared to the 430,000 miles per hour achieved by the Parker Solar Probe, but the scales are different. The probe's speed was measured relative to an object it was approaching over millions of miles. Andromeda's speed is measured relative to an object it is approaching over millions of light-years. Converting to consistent units, 110 kilometers per second equals roughly 246,000 miles per hour, a respectable fraction of the probe's velocity sustained not for a brief flyby, but for a continuous approach lasting billions of years. At this rate, Andromeda closes the distance to the Milky Way by roughly 3.5 billion kilometers per year, about 23 astronomical units, roughly the distance from the Sun to Uranus. Viewed from this perspective, the approach is visually imperceptible, but gravitationally relentless. Every year, the tidal influence of Andromeda on the Milky Way strengthens slightly. Every year, the outer reaches of our galactic halo feel a marginally stronger pull toward the approaching giant. Every year, the inevitable collision grows slightly more imminent. The first close passage between the two galactic cores will occur in approximately 4.5 billion years. The full merger, the gravitational relaxation of the combined system into a single elliptical galaxy, will require perhaps 6 billion years more. These timescales are so long that they mock human intuition. 4.5 billion years ago, the Earth had just finished forming from the protoplanetary disk surrounding the young Sun. The first single-celled organisms would not appear for another 500 million years. Multicellular life would wait another 3 billion years. Human civilization emerged 10,000 years ago, approximately 0.02% of the time remaining before the collision. Everything that humanity has ever known, every empire and every extinction, every ice age and every warming, occupies a period so brief relative to the merger timescale that it would not appear as even a single pixel on a timeline stretching from now until first passage. Yet the physics of the merger can be understood and predicted with remarkable precision. Computer simulations of galactic collisions have matured over the past 4 decades from crude N-body models, with a few thousand particles, to sophisticated hydrodynamic calculations, incorporating millions of resolution elements, realistic gas physics, star formation, black hole growth, and feedback processes. These simulations can follow the evolution of merging galaxies from initial approach through final coalescence, generating predictions for what the night sky will look like, what new stars will form, what happens to existing planetary systems, and how the supermassive black holes at the centers of each galaxy will eventually find each other and merge. The simulations reveal a sequence of events that unfolds over billions of years but follows a predictable choreography. The first act is the approach, the phase we are currently experiencing, during which the two galaxies fall toward each other under their mutual gravity. As they draw closer, tidal forces begin to distort each disk. Long streamers of stars are pulled from the outer regions, forming tidal tails that extend hundreds of thousands of light years into space. These tails are the most photogenic features of merging galaxies, and images of real galaxy pairs like the antennae galaxies or the mice galaxies show exactly such structures. Thin bridges of stars stretch between the colliding systems and curved tails swept back by the gravitational tide. The second act is the first close passage. The galactic cores, dense concentrations of stars surrounding each supermassive black hole, approach within tens of thousands of light years of each other. They do not collide on this first passage, but swing past each other in a hyperbolic encounter, each deflecting the trajectory of the other. The disks of both galaxies are violently disturbed. Stars that were quietly orbiting in the galactic plane are scattered into the halo. Gas that was distributed throughout each disk is compressed and shocked, triggering a burst of star formation that can increase the rate of new star creation by factors of 10 or more. This is the starburst phase, a brief but brilliant period during which the merging system produces new stars at a prodigious rate, using up gas that would otherwise have fueled gentler star formation over billions of years. After the first passage, the two galactic cores continue on their paths, now gravitationally bound to each other, but still separated by hundreds of thousands of light years. They reach maximum separation and then fall back toward each other for a second passage. This second encounter is even more violent than the first. More stars are scattered, more gas is compressed. The star formation rate spikes again. The process repeats, with each subsequent passage bringing the cores closer together, each passage stripping away more of the coherent structure of the original disks, each passage converting more of the galaxy's gravitational potential energy into the random motions of heated stars and gas. This phase of repeated close passages can last for billions of years, with the galactic cores oscillating around each other like a pair of weights attached to a spring that is gradually dissipating its energy. The mechanism for this energy dissipation is dynamical friction, a gravitational process by which a massive object, moving through a sea of smaller masses, loses momentum by deflecting those masses into its wake. The The supermassive black holes at the centres of each galaxy, surrounded by their dense nuclear star clusters, experience this friction as they plunge through each other's stellar populations. With each passage, they lose orbital energy. With each passage, their maximum separation decreases. Eventually, inevitably, they spiral together. The final merger of the supermassive black holes is one of the most dramatic events in the universe. The Milky Way's central black hole has a mass of approximately 4 million solar masses. Andromeda's central black hole is larger, perhaps 100 million solar masses or more, though estimates vary. When these black holes approach within a few light years of each other, dynamical friction becomes inefficient. The stellar background that was slowing them down becomes too sparse. A new mechanism must take over to bring them the final distance to coalescence. This mechanism is gravitational wave emission. As two massive objects orbit each other, they produce ripples in space-time, gravitational waves that carry energy away from the system. This energy loss causes the orbit to shrink. For stellar mass black holes merging after the death of massive stars, this process can take billions of years. For supermassive black holes separated by light years, it would take longer than the age of the universe. But as the orbit shrinks, the gravitational wave emission intensifies. The energy radiated scales as the fifth power of the orbital velocity, which means a factor of 2 reduction in orbital separation leads to roughly a factor of 32 increase in energy loss. The process accelerates. The final in-spiral from a separation of about 1/1000th of a light year to merger takes only a few million years. The final plunge from close orbit to coalescence takes only hours. At the moment of merger, the gravitational wave emission reaches its peak. For a system combining a 4 million solar mass black hole with a 100 million solar mass black hole, the gravitational wave luminosity in the final moments exceeds the combined electromagnetic luminosity of every star in the observable universe. More energy streams away in gravitational waves during those last few orbits than the Sun will emit in its entire 10 billion year lifetime. This is energy released by the conversion of orbital motion into the fabric of spacetime itself, ripples propagating outward at the speed of light, slightly squeezing and stretching every object they pass through, including any planets that still orbit stars in the merged galaxy. The gravitational waves from supermassive black hole mergers are too low in frequency to be detected by ground-based observatories like LIGO, which are sensitive to the higher frequency waves produced by stellar mass black hole mergers, but they should be detectable by pulsar timing arrays, networks of millisecond pulsars distributed across the sky, whose signals are monitored for the tiny delays and advances caused by passing gravitational waves. In fact, recent observations from pulsar timing arrays have detected a background hum of gravitational waves, almost certainly produced by the combined signal of thousands of supermassive black hole pairs throughout the universe, all spiraling toward merger. The merger of the Milky Way and Andromeda's central black holes, when it finally occurs some 6 billion years hence, will add to this cosmic background, a single loud event superimposed on the stochastic murmur. The galaxy that emerges from this merger will bear little resemblance to either of its progenitors. Astronomers have given it various unofficial names, most commonly Milkomeda or Milkdromeda, though neither has achieved universal adoption. Whatever it is called, it will be an elliptical galaxy, a vast spheroidal collection of old stars orbiting chaotically around a common centre of mass. The disk structure that characterises the Milky Way today, with its spiral arms and thin stellar plane, will be gone. The dusty lanes of star-forming regions that thread through Andromeda's disk will be dispersed. The merger process converts disk galaxies into elliptical galaxies by heating the stellar orbits, replacing the organised circular motion of disk stars with the random three-dimensional motion of elliptical galaxy stars. This transformation explains a puzzle that long perplexed astronomers studying the populations of galaxies in the universe. Elliptical galaxies are most common in the densest environments, the centres of galaxy clusters where collisions are frequent. Spiral galaxies are most common in the field, in the sparse regions between clusters where collisions are rare. The connection is now understood as evolutionary. Spiral galaxies are the pristine form, the natural outcome of gas collapsing and spinning up into a disk, where star formation proceeds in an orderly fashion. Elliptical galaxies are the processed form, the remnants of merger events that scrambled the original disk structure. Every elliptical galaxy contains the ghosts of the spiral galaxies from which it was built. The Milky Way and Andromeda, two of the most magnificent spiral galaxies in the local universe are destined to become one such ghost. For observers on Earth, if Earth still exists by the time of the merger, the visual spectacle will be extraordinary. The merger process will unfold so slowly that no human lifetime could perceive the change, but time-lapse visualizations spanning millions of years would show Andromeda swelling in the sky from its current faint smudge visible to the naked eye on dark nights to a sprawling band of light rivaling and then surpassing the Milky Way itself. The night sky will fill with the light of hundreds of billions of stars as the two galactic disks interpenetrate. Tidal tails will stretch across the heavens, thin arcs of stars marking the gravitational disruption of both galaxies. During the starburst phases triggered by gas compression, luminous young star clusters will blaze in regions where gas clouds have collided and collapsed. The Sun itself will likely survive the merger in a physical sense. Direct stellar collisions are too improbable to pose a serious threat, but the Sun's orbit within the merged galaxy will be dramatically altered. Simulations suggest approximately a 10% probability that the solar system will be thrown into one of the tidal tails, ending up hundreds of thousands of light-years from the merged galactic centre, perhaps even ejected entirely into intergalactic space. There is a small but non-zero probability that the solar system could be captured by Andromeda's gravity during the first close passage, transferred from one galaxy to the other before the final coalescence. Most likely, the Sun will end up on a chaotic orbit within the merged elliptical galaxy, neither in a well-defined disk nor ejected into the void, simply one of trillions of stars scattered through the stellar halo of Milky. None of this will matter to life on Earth, however. By the time of the first close passage between the Milky Way and Andromeda, approximately 4.5 billion years from now, the Sun will be approaching the end of its main sequence lifetime. It will have expanded to become a red giant, its outer atmosphere engulfing the inner planets, its luminosity so greatly increased that Earth's oceans will have long since boiled away. Life as we know it will have ended billions of years before the galactic merger begins in earnest. The collision of galaxies and the survival of terrestrial biology occupy different chapters of the cosmic story, chapters separated by timescales that dwarf anything in human experience. But we can imagine other observers, beings evolved on planets orbiting younger stars in the merged galaxy, looking back at the history of their home and marvelling at the violence that created it. They might detect in the stellar populations the signature of the ancient merger, finding stars that bear the chemical fingerprints of what was once the Milky Way orbiting alongside stars that bear the fingerprints of what was once Andromeda. They might map the orbits of hypervelocity stars and trace them back to close encounters with the binary supermassive black hole that briefly existed at the merged galaxy's centre. They might discover, in their own sky, the descendants of the lonely intergalactic stars that once drifted through the void between the two progenitor galaxies, now incorporated into the common stellar population of a single vast system. And so the collision between the Milky Way and Andromeda represents not an ending but a transformation. Two galaxies will become one. Trillions of stars will be rearranged into new configurations. Two supermassive black holes will spiral together and merge in an event that outshines the entire visible universe in gravitational wave luminosity. Gas that currently floats between the galaxies will be incorporated into the merged system, compressed and shocked and converted into new generations of stars. The void between the Milky Way and Andromeda, that vast emptiness that seems so permanent when viewed on a human timescale, is in fact a temporary condition, a transient phase in the gravitational evolution of the local group. This transformation has already begun in the most tenuous outer reaches of each galaxy's halo. It will proceed through the increasing interpenetration of the circumgalactic media, the eventual collision of the gas-rich disks, the merger of the dark matter halos, and finally the coalescence of the central black holes. Each stage involves the restructuring of matter and energy across scales from atoms to astronomical units to megaparsecs. The restructuring unfolds across timescales that stretch the imagination beyond its comfortable limits. A human lifetime, measured against the duration of this merger, represents less than a single frame in a film that runs for billions of years. Yet within that incomprehensible duration, every moment of the transformation follows the same physical laws that govern the fall of an apple or the orbit of a satellite. The difference is not one of kind, but of scale, not of physics, but of patience. And understanding this transformation requires us to examine what happens not in the bright cores of the colliding galaxies, not in the spectacular starbursts that will illuminate the merger, but in the spaces between, in the vast volumes that currently separate the Milky Way from Andromeda, and that will, over the coming eons, be systematically erased. Consider the journey of a single hydrogen atom currently drifting in the deepest intergalactic void between the two galaxies. This atom has existed in its present form for perhaps 10 billion years, a relic of the primordial gas that filled the universe before the first stars ignited. It has never been incorporated into a star, never been processed through nuclear fusion, never been part of a planet or a living thing. It drifts at perhaps 10 kilometers per second relative to the local standard of rest, a velocity that would carry it from New York to Los Angeles in roughly 6 minutes, but that represents, on cosmic scales, virtual stillness. In the billions of years since it first condensed from the primordial plasma, this atom has travelled perhaps 300,000 light-years, a distance that sounds vast but that represents less than 15% of the current gap between the Milky Way and Andromeda. This lonely atom is not alone. It is surrounded by perhaps 100 similar atoms per cubic metre, a density so low that if you searched a volume the size of Earth, you would find only a few trillion atoms total, less matter than exists in a single human cell. Yet across the 2.5 million light-year gap between the galaxies, these sparse atoms accumulate into a mass equivalent to hundreds of millions of suns. The void is not empty. It is merely diffuse beyond ordinary comprehension. As the galaxies approach each other, this atom's fate will change. The gravitational field in which it drifts will shift. The balance between the Milky Way's pull and Andromeda's pull will tilt first one way, then the other, then become increasingly chaotic as the two galaxies interpenetrate. The atom will find itself no longer in a void between two distinct systems, but within a single, larger, more turbulent environment. Gas that was once part of Andromeda's circumgalactic medium will flow past it. Shock waves from distant collisions will eventually reach its position, compressing the gas around it, raising its temperature, perhaps ionizing it into a plasma once more. After 10 billion years of cold isolation, the atom may find itself incorporated into a collapsing gas cloud, compressed along with millions of its neighbours into a protostellar core, finally experiencing the nuclear fusion that transforms hydrogen into helium and releases the energy that powers stars. The probability of any individual atom experiencing this transformation is small. Most of the intergalactic hydrogen will remain diffuse, even after the merger, incorporated into the hot halo of the elliptical galaxy that results but never compressed into stars. Yet the sheer number of atoms involved means that enormous quantities of previously intergalactic gas will eventually participate in star formation. The merger does not merely rearrange existing stars, it creates new ones from material that has waited since the beginning of time for the conditions that allow stellar birth. This process of gas incorporation and stellar creation connects to one of the most profound questions in astrophysics, the cosmic star formation history and its eventual end. The universe's rate of star formation peaked approximately 10 billion years ago, when galaxies were smaller, denser, and more gas-rich than they are today. Since that ancient maximum, the cosmic star formation rate has declined steadily, as galaxies have consumed their gas reservoirs and as the expansion of the universe has reduced the rate at which new gas falls into galactic halos. The Milky Way currently forms new stars at a rate of roughly 1 to 2 solar masses per year, a modest output compared to the starbursts of the distant past. The merger with Andromeda will temporarily reverse this decline. When the gas disks of the two galaxies collide, the compression and shock heating will trigger a starburst that may increase the star formation rate by a factor of 10 or more. For a few 100 million years, the merged system will blaze with the light of young stellar populations, blue giant stars and their associated nebulae illuminating gas that has finally found the conditions for collapse. This starburst will consume the available gas at a prodigious rate, converting the raw material of future stars into actual stars far faster than the leisurely pace of isolated galactic evolution would allow. But this burst of creativity carries within it the seeds of its own ending. By consuming the gas supply so rapidly, the starburst hastens the day when no more gas remains for star formation. The merged galaxy will transition from a site of active stellar birth to a quiescent elliptical galaxy, dominated by aging stellar populations. The young blue stars born in the merger starburst will evolve and die. The intermediate mass stars will become white dwarfs. The massive stars will explode as supernovae, briefly illuminating the merged galaxy before fading into neutron stars and black holes. And with no new star formation to replace the dying generations, the galaxy will gradually dim as its remaining stars consume their nuclear fuel and fade into stellar remnants. This transition from star forming to quiescent represents one of the great one-way doors of cosmic evolution. Once a galaxy has consumed or expelled its gas supply, there is no mechanism to restore it on any reasonable timescale. Gas can flow in from the intergalactic medium, but the rate of such inflow decreases over cosmic time as the universe expands and the reservoirs of available gas are depleted. The merger between the Milky Way and Andromeda will produce a magnificent starburst, but it will also accelerate the transformation of the local group from a site of ongoing cosmic creation to a slowly fading fossil of a more active past. The mathematics of this transformation can be expressed in terms of gas consumption timescales. The current gas content of the Milky Way, including both the cold molecular gas in the disk and the hot ionized gas in the halo, totals perhaps 50 billion solar masses. At the current star formation rate of 1 to 2 solar masses per year, this gas supply would last for roughly 30 billion years if star formation continued at a constant rate. But the merger starburst will not preserve this leisurely pace. If the star formation rate increases to 20 solar masses per year and is sustained for several 100 million years, the gas consumption timescale shrinks dramatically. The merged galaxy may exhaust its star-forming material within a few billion years of the merger's completion, far sooner than either the Milky Way or Andromeda would have done in isolation. There is a profound irony in this acceleration. The collision of two gas-rich spirals produces more stars than either would have created alone, but it also ends star formation sooner. The merger is simultaneously creative and destructive, generating new stellar populations while ensuring that the epoch of star formation will conclude more abruptly than it otherwise would have. The cosmos giveth and the cosmos taketh away, and in the arithmetic of galactic evolution, the giving and the taking often occur together. Yet even this accelerated exhaustion of star-forming material operates on timescales that dwarf anything in human experience. The merger starburst will last hundreds of millions of years. The subsequent decline will take billions of years more. The final fading of the last stars in the merged galaxy lies so far in the future that the current age of the universe is a small fraction of the time that will pass before it occurs. We are witnessing, in the approach of Andromeda, the opening movement of a symphony that will not reach its final notes for perhaps 100 trillion years. The involvement of intergalactic matter in this transformation extends beyond simple hydrogen gas. The dark matter that fills the space between the Milky Way and Andromeda will participate in the merger in ways that fundamentally shape the final structure of the merged system. Dark matter cannot radiate energy, cannot dissipate its kinetic energy through collisions in the way that ordinary matter does. When two dark matter halos merge, the particles that compose them pass through each other like two swarms of bees, their orbits becoming entangled through gravitational interaction rather than through physical contact. This difference between dark matter and ordinary matter produces a characteristic signature in merging systems. The gas, which can dissipate energy through radiation, tends to sink toward the centres of the merging halos. The dark matter, which cannot dissipate energy, remains more extended, forming a large diffuse halo around the concentrated ordinary matter. In the merged system that will result from the Milky Way-Andromeda collision, the dark matter will form a roughly spherical halo extending perhaps 1 million light-years from the centre, while the stars and gas will be concentrated in a much smaller central region, perhaps 100,000 light-years across. This separation of dark matter from ordinary matter creates an observational signature that astronomers can use to study mergers in other systems. In clusters of galaxies where multiple mergers have occurred, the dark matter and the hot gas sometimes become spatially separated, with the dark matter moving ahead of the gas as the merger proceeds. The most famous example of this phenomenon is the Bullet Cluster, a pair of galaxy clusters that collided approximately 150 million years ago, and that show clear separation between the dark matter, detected through its gravitational lensing of background galaxies, and the hot gas, detected through its X-ray emission. The Bullet Cluster provides some of the strongest direct evidence for the existence of dark matter, demonstrating that the bulk of the mass in these systems moves independently of the ordinary matter that produces the X-ray emission. The merger between the Milky Way and Andromeda will not be observable in the same way as the bullet cluster, both because we are inside the system and because the collision geometry differs from that of the bullet cluster. But the same physics will apply. The dark matter halos will interpenetrate and eventually merge, while the gas experiences compression and shock heating at the collision interface. The final merged halo will contain dark matter particles that originated in both progenitor systems, thoroughly mixed by billions of years of gravitational interaction, their original allegiances erased by the chaos of the merger process. The distribution of dark matter in the merged system will determine much of its long-term gravitational evolution. Stars that orbit through the dark matter halo will experience gravitational perturbations from the invisible mass, their orbits gradually evolving under the influence of forces that cannot be seen directly, but that can be inferred from stellar motions. The study of stellar kinematics in elliptical galaxies, the measurement of how far stars are moving and in what directions, reveals the presence of dark matter even in systems where no other evidence would suggest its existence. The stars are responding to gravitational forces from matter that emits no light, and the pattern of their response traces out the invisible architecture of the dark matter halo. Within the intergalactic space between the Milky Way and Andromeda, dark matter already forms structures that will influence the merger's development. Cosmological simulations reveal that dark matter is not distributed uniformly, but instead forms a complex web of filaments and voids, with matter flowing along the filaments toward nodes where galaxies and galaxy clusters form. The local group sits within this cosmic web, connected to surrounding structures by dark matter filaments that channel the flow of matter on scales of tens of millions of light years. The space between the Milky Way and Andromeda is threaded by these filamentary structures. Dark matter flows along the filaments, and ordinary matter follows the gravitational guidance that the dark matter provides. Gas that will eventually participate in the merger is already moving along these filamentary highways, pulled toward the local group's gravitational centre by forces that have been operating since the filaments first formed in the early universe. The merger is not merely a collision between two isolated systems, it is the local manifestation of a cosmic process that shapes structure on the larger scales, the hierarchical assembly of matter into ever larger concentrations under the relentless action of gravity. The behaviour of the intergalactic medium during the merger will be influenced by processes that operate on scales far larger than the local group itself. The temperature and density of gas between the Milky Way and Andromeda reflect the balance between gravitational heating, which raises the temperature as gas falls into potential wells, and radiative cooling, which lowers the temperature as gas emits photons and loses energy. In regions where cooling dominates, gas can condense into denser structures and eventually form stars. In regions where heating dominates, gas remains hot and diffuse, unable to collapse under its own gravity. The current intergalactic medium between the Milky Way and Andromeda is too hot and too diffuse for star formation to occur. The temperature exceeds 100,000 Kelvin, far too hot for hydrogen to form molecules, and far too hot for gravitational collapse to overcome thermal pressure. This gas represents a reservoir of material that has not yet participated in star formation, waiting for conditions that will allow it to cool and condense. The merger will create those conditions, at least in some regions, by compressing the gas and allowing it to radiate away its thermal energy more efficiently. The physics of gas cooling involves a complex interplay of atomic processes. Hot gas radiates energy primarily through the excitation and de-excitation of electrons in partially ionized atoms. When an electron in an ion absorbs energy from a collision with another particle, it jumps to a higher energy level. When it falls back to its original level, it emits a photon that carries energy away from the gas. This process is most efficient at temperatures where the gas contains a mixture of neutral and ionized atoms, roughly 10,000 to 1,000,000 Kelvin depending on the composition of the gas. At higher temperatures, the gas is fully ionized and the cooling mechanisms are less efficient. At lower temperatures, the gas is mostly neutral, and different cooling mechanisms involving molecular hydrogen or dust grains become important. The merger will drive gas through a range of temperatures as shock waves compress and heat the intergalactic medium. Some of this gas will be heated to temperatures of tens of millions of Kelvin, joining the hot halo that surrounds the merged galaxy. Some will be compressed but cool rapidly, condensing into dense clouds that can collapse to form stars. The balance between these outcomes will determine how much of the intergalactic gas participates in the merger starburst and how much remains in the hot halo, unavailable for star formation. Observationally, the merger will eventually produce signatures across the electromagnetic spectrum. Hot gas will emit X-rays, detectable by space telescopes designed to observe the high-energy universe. Warm ionized gas will produce emission lines in the ultraviolet and optical, traceable through spectroscopic observations. Cold molecular gas will emit radio waves at millimeter and submillimeter wavelengths, revealing the dense clouds where star formation is actively occurring. The merged galaxy will be a multi-wavelength laboratory, its structure and dynamics encoded in photons spanning 12 orders of magnitude in wavelength. But these observations lie 4.5 billion years in the future. No human eye will witness the merger directly. No human instrument will record the X-ray emission from the shock-heated gas or the radio emission from the star-forming clouds. The transformation of the intergalactic void into the interior of a merged galaxy will occur without any human witness, a cosmic drama played out in an empty theatre. This raises questions that transcend astrophysics and venture into philosophy. What is the significance of an event that no one observes? Does the merger between the Milky Way and Andromeda matter if no conscious being ever perceives it directly? These questions have no scientific answers, but they illuminate the peculiar position of humanity in the cosmic story. We are aware of processes that operate on timescales vastly longer than our species will likely exist. We can predict the future of our galaxy for billions of years, even though we have no expectation of participating in that future. Our knowledge extends beyond the boundaries of our existence, giving us a strange and perhaps unique perspective on the universe we inhabit. The intergalactic space between the Milky Way and Andromeda offers a particularly stark example of this cosmic irony. The void that separates us from our nearest large neighbour seems empty to the casual observer, devoid of interest or significance. But careful investigation reveals it to be filled with matter, with energy, with complex structures and dynamic processes that connect the two galaxies even now. The void is already part of the local group's gravitational evolution, already participating in the slow collapse that will eventually bring the galaxies together. And in this participation lies a final insight. The distinction between the galaxies and the void, between matter and emptiness, between activity and quiescence, is ultimately one of degree rather than kind. There is no sharp boundary where the Milky Way ends and intergalactic space begins. Instead, there is a continuous gradient of density, from the crowded stellar disk at the centre to the sparse dark matter halo at the edge, to the nearly empty void at the current midpoint between the galaxies. Every point along this gradient is part of the same gravitational system. Every atom, whether in the core of a star or drifting alone in the deepest void, responds to the same forces and participates in the same evolution. The merger between the Milky Way and Andromeda will erase the artificial distinctions we have drawn. Two spiral galaxies will become one elliptical galaxy. Two halos will become one halo. Two voids, the space beyond the Milky Way and the space beyond Andromeda, will merge into the uniform emptiness that surrounds the combined system. The hierarchical structure of the local group will simplify, two major galaxies plus dozens of satellites becoming a single dominant system, orbited by whatever dwarf galaxies survive the tidal disruption of the merger. And in this simplification lies the deepest truth about intergalactic space, a truth that extends far beyond our local cosmic neighbourhood and speaks to the fundamental nature of the universe itself. The void between the Milky Way and Andromeda is not merely a local phenomenon, not simply an accident of our particular cosmic address. It is a representative sample of the space that comprises most of the observable universe. When we study the 2.5 million light-years that separate us from Andromeda, we are studying the dominant component of cosmic structure. We are examining the emptiness that holds the fullness, the darkness that frames the light, the silence in which the music of the spheres plays out across unimaginable distances. Consider the broader context in which our local void exists. The Milky Way and Andromeda are members of the local group, a modest collection of perhaps 80 galaxies gravitationally bound to one another. But the local group itself is a small component of an immensely larger structure. We reside in the Laniakea supercluster, a collection of approximately 100,000 galaxies spanning 500 million light-years. Laniakea, in turn, is one of approximately 10 million superclusters in the observable universe, each one a vast agglomeration of galaxies separated from its neighbours by even vaster expanses of nearly empty space. The voids between superclusters dwarf the space between the Milky Way and Andromeda by factors of hundreds. The Boötes void, one of the largest known structures of its type, spans approximately 330 million light-years. The KBC void, within which our own local group may reside according to some measurements, extends for nearly 2 billion light-years. These supervoids contain almost nothing by galactic standards, a sphere of space that would comfortably hold thousands of galaxies if it matched the average cosmic density, instead contains perhaps a dozen lonely systems, scattered like motes of dust in an enormous empty room. And yet, even these supervoids are not truly empty. They contain the same constituents we have discovered in the space between the Milky Way and Andromeda, merely at lower densities. Dark matter permeates the voids, its gravitational influence shaping the walls and filaments that bound the empty regions. Diffuse hydrogen drifts through the darkness, ionized by the cosmic ultraviolet background and slowly participating in the universe's thermal evolution. The intergalactic medium extends through even the emptiest regions, connecting all of cosmic structure in a tenuous but continuous web. This is the revelation that transforms our understanding of the universe. Space is not a container in which matter floats. Space and matter are interpenetrating aspects of a single reality. The vacuum of physics is not the void of everyday intuition. It is a dynamic, energetic, structured environment that participates actively in cosmic evolution. The emptiness between galaxies is not an absence but a presence, not a negation but an affirmation of the universe's fundamental unity. The merger between the Milky Way and Andromeda, when it finally occurs, will demonstrate this unity in spectacular fashion. But we need not wait 4.5 billion years to appreciate the lesson. We can observe similar mergers occurring now, in other galaxy groups scattered throughout the observable universe. We can watch the process unfold in real time, albeit in other cosmic neighbourhoods, and extrapolate what we learn to our own future. The antennae galaxies, NGC 4038 and NGC 4039, provide perhaps the most famous example. Located approximately 45 million light-years from Earth in the constellation Corvus, these two spiral galaxies are approximately 300 million years into a collision that began when their separation was similar to the current distance between the Milky Way and Andromeda. Today, they are thoroughly enmeshed, their spiral arms distorted into sweeping tidal tails that extend for hundreds of thousands of light-years into surrounding space. The intergalactic void that once separated them has been transformed into a collision zone. The diffuse gas that filled the space compressed into dense clouds, where star formation proceeds at prodigious rates. Observations of the antennae reveal what we might expect from our own future merger. The collision has triggered starbursts that produce new stars at rates 10 to 20 times higher than either galaxy experienced in isolation. The compressed gas has fragmented into thousands of star clusters, some of them massive enough that they will survive as globular clusters, orbiting the eventual merger remnant for billions of years. The gravitational interaction has flung material outward into tidal streams that will rain back onto the merged system over the next several 100 million years, extending the period of enhanced star formation long after the initial collision has passed. But the antennae also reveal the complexity we should expect. The two nuclei of the original galaxies remain distinct, separated by approximately 30,000 light-years, and still orbiting their common centre of mass. The supermassive black holes at their centres have not yet merged, that cataclysmic event still hundreds of millions of years in the future. The dark matter halos have interpenetrated but not yet fully relaxed into a single equilibrium structure. The merger is ongoing, a process rather than an event, and the final state lies far in the future even for a system that began its collision hundreds of millions of years ago. Closer examination reveals another crucial detail. The intergalactic space that once separated NGC 4038 and NGC 4039 did not simply disappear when the galaxies collided. It was incorporated into the merged system, its gas becoming part of the interstellar medium, its dark matter becoming part of the combined halo. The void was not destroyed but transformed. the emptiness became fullness through the simple expedient of drawing in material from the surrounding environment and converting gravitational potential energy into the kinetic energy of stellar motions and the thermal energy of heated gas. This transformation is universal. Every galaxy merger in the history of the universe has involved the conversion of intergalactic space into galactic interior. Every elliptical galaxy we observe today formed through the accumulation of smaller systems, the voids between those systems becoming the interior of the final product. The Milky Way itself was built through hundreds of such mergers, smaller galaxies and their surrounding voids being incorporated into the growing disk and halo. The atoms in your body, forged in ancient stars, may once have drifted through intergalactic space before being captured by the Milky Way's gravitational embrace. This cosmic recycling connects the present to the past and to the future. The void between the Milky Way and Andromeda will not persist forever. In 4.5 billion years it will become the interior of Milkomeda, just as earlier voids became the interior of our current galaxy. And Milkomeda itself will eventually merge with other members of the local group, incorporating still more intergalactic space into its growing bulk. The process continues indefinitely, limited only by the expansion of the universe, which eventually carries other galaxy groups beyond the gravitational reach of the local group. This expansion introduces the final and most profound element of the cosmic drama. The universe is not static. It has been expanding since the Big Bang 13.8 billion years ago, and observations indicate that this expansion is accelerating. Driven by a mysterious component called dark energy, which constitutes approximately 68% of the total energy density of the universe, space itself is stretching at an ever-increasing rate. The consequences for intergalactic space are both subtle and profound. For gravitationally bound systems like the local group, cosmic expansion has minimal effect. The gravitational attraction between the Milky Way and Andromeda, and between these galaxies and the smaller members of the local group, is strong enough to overcome the expansion of space. The local group will continue to collapse even as the universe as a whole expands. Milkomeda will form as predicted, regardless of what happens on larger scales. But for more distant structures, the situation is radically different. Galaxy groups and clusters that are not gravitationally bound to the local group are being carried away by the expansion of space. The intergalactic voids between superclusters are growing larger with each passing moment, and because the expansion is accelerating, these distant structures are receding at ever-increasing velocities. Eventually they will cross the cosmic event horizon, the distance beyond which light can never reach us, and will be forever lost to observation. The timeline of this cosmic isolation is staggering but calculable. In approximately 100 billion years, almost all galaxies outside the local group will have receded beyond the observable universe. The night sky, such as it will contain only the stars of Milkomeda and its surviving satellite galaxies. The intergalactic voids that we can currently study, the spaces between other galaxy groups that provide independent examples of the processes we have explored, will be inaccessible. The cosmic web, the grand structure of filaments and voids that connects all of observable reality, will have fragmented into isolated islands surrounded by truly empty space so empty that no observation could ever reveal what lies beyond. This is the ultimate fate of intergalactic space, at least on the larger scales. The voids will grow without limit, stretched by the expansion of the universe, until they contain effectively nothing detectable. The tenuous hydrogen that currently threads through the emptiness will be diluted to the point where individual atoms are separated by distances measured in light years. The gravitational influence of distant structures will fade to unmeasurable levels, as those structures recede beyond the cosmic horizon. The universe will become, in a very real sense, emptier than it has ever been, even as the spaces within gravitationally bound systems become fuller through successive mergers. This divergent evolution, local collapse into ever denser structures accompanied by large-scale expansion into ever greater emptiness, is perhaps the most profound paradox of modern cosmology. The universe is simultaneously becoming more and less empty, depending on which scales one considers. The intergalactic space between the Milky Way and Andromeda exemplifies the collapsing half of this dichotomy, destined to become the interior of a merged galaxy. But the intergalactic space between the local group and distant superclusters exemplifies the expanding half, destined to grow without bound until it separates us from the rest of cosmic structure entirely. In this context, our current era assumes a special significance. We live at a moment in cosmic history when the observable universe is maximally rich, when the largest number of galaxies can be observed and studied, when the cosmic web remains connected and explorable. In the distant future, astronomers on some planet orbiting a star in Milky Way will have no way of knowing that the universe extends beyond their immediate cosmic neighbourhood. The evidence for the Big Bang, for the existence of other galaxy groups, for the vast web of structure that we can currently map, will have been carried beyond the cosmic horizon by the expansion of space. We are, in a sense, the last generation of cosmic beings with access to the full picture. Our telescopes can see back to the earliest epochs, can detect the cosmic microwave background, can map billions of galaxies scattered across cosmic history. This will not always be possible. The information we have gathered about the universe's large-scale structure, about its history and evolution, is information that will become increasingly difficult and eventually impossible to obtain as the expansion carries evidence beyond our reach. This adds weight to the endeavour of understanding intergalactic space, to the careful observations and theoretical models that reveal the structure hidden within apparent emptiness. We are not merely satisfying curiosity, we are preserving knowledge that will be irreplaceable. Every measurement of the intergalactic medium, every map of dark matter distribution, every model of the cosmic web's evolution contributes to a record that becomes more precious with each passing eon. And within this grand context, the void between the Milky Way and Andromeda assumes a particular significance. It is the intergalactic space closest to us, the emptiness most accessible to our instruments, the void that will ultimately become our cosmic home. Every lesson we learn from its study applies to the broader universe, but the study itself is intimate, focused on the space through which our galaxy has been falling for billions of years and will continue to fall for billions more. The hypervelocity stars we discussed, flung between the galaxies by gravitational interactions, are messengers from this void. They have sampled the emptiness through which they travel, their properties shaped by their journey through intergalactic space. Future observations may detect more of these stellar wanderers, mapping the void through their trajectories and compositions. They are, in a sense, probes sent by nature to explore regions that our spacecraft will never reach. The gas that fills the void, diffuse and difficult to detect, will eventually power the star formation of the merged galaxy. The hydrogen atoms drifting through the darkness today will, in 5 or 6 billion years, be incorporated into molecular clouds where new stars form. Some of those atoms will find themselves in the cores of new stars, fused into heavier elements that will be scattered into space by stellar winds and supernovae. Some will end up in planets, in oceans, perhaps even in the bodies of whatever beings might arise in the distant future of Milky Way. The dark matter that dominates the void by mass will shape the gravitational potential of the merged system, determining the orbits of stars and gas clouds for billions of years to come. The invisible scaffolding that currently spans the space between the galaxies will become the invisible scaffolding within the merged galaxy, its presence detectable only through the motions it induces in visible matter. All of this, every atom and particle, every field and force, is already part of the system we call the local group. The boundaries we draw between galaxies and voids, between matter and emptiness, are artifacts of our perspective, useful for description but ultimately arbitrary. The universe does not recognize these distinctions. It sees only density and energy, only force and motion, only the continuous distribution of matter across cosmic scales. This is perhaps the deepest insight that intergalactic space offers. The void is not a hole in the universe, it is part of the universe, as fundamental and significant as the galaxies that punctuate it. The emptiness has structure, has dynamics, has a story that connects the beginning of cosmic time to its eventual end. To dismiss the void as merely empty is to miss most of what the universe actually is. For when we tally the contents of the cosmos, we find that the spaces between galaxies contain more than the galaxies themselves. The intergalactic medium holds approximately 40% of all ordinary matter. Dark matter fills the voids in concentrations that dwarf its presence in galactic disks. Dark energy, if it permeates space uniformly as most models suggest, is distributed equally between regions we call full and regions we call empty. By most measures, the void is where the universe actually happens. And so we return to where we began, to the 2.5 million light-years that separate the Milky Way from Andromeda. to the apparent emptiness that beckons across the cosmic gulf. We have journeyed through this space in imagination, guided by the instruments that probe it and the theories that interpret what they find. We have discovered that the void is not void, that the emptiness is not empty, that the nothing is in fact everything we had been missing. The intergalactic medium breathes with the rhythm of the cosmic background, ionized hydrogen pulsing with photons from the epoch of reionization. The dark matter web stretches between the galaxies like the skeleton of a bridge not yet built, its presence known only through gravity's patient insistence. Hypervelocity stars streak through the darkness, travellers without destination, carrying with them the chemical signatures of their home galaxies and the kinetic memories of the violent encounters that flung them into exile. And through it all, the great convergence continues. The Milky Way falls toward Andromeda at 110 kilometres every second, a motion so slow on human scales that we cannot perceive it, yet so persistent that it will transform the cosmos we know into something utterly different. The void shrinks with each passing moment, the emptiness filling with the light of two galaxies drawing inexorably together. This is not a catastrophe, but a culmination. For billions of years, the matter that will become Milkomeda has been scattered across hundreds of thousands of light years, separated into distinct structures that we call the Milky Way, Andromeda, and the spaces between them. The merger will reunite this matter, will bring together components that have been apart since the early universe, will create a single system from the fragments of cosmic history. In the deepest sense, the intergalactic void between our galaxy and Andromeda is not a barrier, but a bridge. It connects rather than separates. The same gravity that holds stars in their orbits and planets around their suns extends through the void, binding the two galaxies together even now. The merger that will occur in 4.5 billion years was determined at the moment of the Big Bang, written into the distribution of matter and energy that emerged from the primordial fireball. Everything that has happened since has been the working out of that initial condition, the slow collapse of structure under gravity's patient guidance. We are privileged to witness a moment in this collapse, a brief window in cosmic history when two great galaxies stand poised on the threshold of union. The void between them is not a permanent feature but a transitional state, a brief interlude between the isolation of the past and the merger of the future. In another 5 billion years there will be no void to contemplate, no emptiness to explore. The question of what fills the space between galaxies will be rendered moot, at least for this particular region of the universe. But until then the void persists, vast and dark and filled with wonders we have only begun to understand. It challenges our intuition at every turn, revealing complexity where we expected simplicity, activity where we expected stasis, presence where we expected absence. It is perhaps the universe's way of teaching humility, of reminding us that our everyday experience of fullness and emptiness provides poor preparation for the realities of cosmic structure. The night sky, when you next look up at it, will appear unchanged. The band of the Milky Way will stretch across the darkness, and somewhere beyond it, invisible to the naked eye but present nonetheless, the glow of Andromeda will continue its ancient fall toward us. The space between will seem empty, a veil of darkness punctuated only by foreground stars. But now you know what lies within that apparent emptiness. You know about the hydrogen halos extending hundreds of thousands of light years from each galaxy, their faint emission almost too dim to detect. You know about the dark matter filaments threading the void, their gravitational influence shaping the paths of everything that has mass. You know about the few stars wandering through the intergalactic darkness, hypervelocity refugees from gravitational encounters too violent to imagine. You know about the cosmic web, the grandest structure in the universe, of which our local void is but a tiny strand. And you know about the future, the merger that will transform everything we see into something new. The void will not last. The emptiness will fill. The nothing will become everything, given only the currency of cosmic time. This is the story of intergalactic space, written in atoms too sparse to see, and gravity too weak to feel, and light too dim to perceive, without instruments of extraordinary sensitivity. It is a story of patience, of processes that operate on timescales so vast that human civilization is but a single heartbeat in their measure. It is a story of unity, of the fundamental interconnection between all things, the seamless web of force and matter that admits no boundaries and recognizes no distinctions between full and empty, between presence and absence, between something and nothing. The universe, we have learned, is not a collection of objects floating in empty space. It is a continuous field of density and energy, varying from place to place but never truly absent. The galaxies are peaks in this field, concentrations of matter that stand out against the background. The voids are troughs, regions where density falls but never reaches zero, and the whole system evolves together, the peaks and troughs interacting through gravity and radiation and the expansion of space itself, producing the cosmos we observe and the future we can predict. Between the Milky Way and Andromeda, this cosmic truth is written in the faintest possible ink. It requires patience to read, and instruments of great subtlety, and minds willing to accept that reality differs from intuition. But for those who make the effort, the reward is profound. The void speaks, and what it says is this: there is no emptiness, only presence waiting to be discovered. There is no nothing, only something too sparse for careless observation to detect. There is no gap in the universe, only gradients in the continuous field of existence. The space between galaxies is not a failure of cosmic creativity. It is instead the canvas on which all cosmic creativity occurs, the context that gives meaning to the structures we call galaxies and stars and planets and people. Without the void, there could be no fullness. Without the emptiness, there could be no presence. The universe requires both, woven together in proportions that allow complexity to emerge from simplicity and life, to arise from matter and minds, to contemplate the vastness of which they are a part. When the Milky Way and Andromeda finally merge, the void between them will vanish, but the lesson it taught will remain. The emptiness was never truly empty. The nothing was always something, and the apparent abyss that separated two island universes was, in truth, the medium through which they were always connected, always falling toward one another, always part of a single gravitational embrace that spans 2.5 million light-years, but admits no true division. The stars are not islands, the galaxies are not isolated, the universe is one.